Good afternoon, sir,
Good morning, good afternoon.
and good afternoon, dear all friends.
Hello, how are you? Must be very now you should relax. Day one is over.
Yes, sir. Yes, sir. How are you, sir?
I'm fine, thank you. Shall we try sharing the screen?
Yes, sir. And
I will try the entire screen.
okay, sir. Okay.
Is it on?
Yes, sir.
Okay. Is it clearly visible? Or the
Yes.
letters are small?
No, no, sir. It is clearly visible.
Okay.
Sir, please press 5. F,
Sorry?
F5. If you press F5, then it will be full screen mode, your PDF.
No, it is not coming. I tried.
Okay.
F5.
Yes, sir. F5.
F5 I did it. Is it coming? It doesn't change my screen.
Yes, sir. It is not changing.
Now?
Now it has changed, sir. Yes.
Okay, so I do control L.
Okay. Okay. Sir, please click here also on the hide.
Sorry?
There is a message meet.google.com is sharing your screen. Click
Yes.
on hide. Click on hide, then it will not show here.
No, I won't hide.
Now just click hide. The only message will go there. Up.
So I hide it. If I hide it, then the message will not be there. Okay.
Okay, sir. Yes, sir. Now you see no message.
You have to hide too many things to use Google.
Yeah. Yes, sir.
It is all the time spying on us.
And for the speaker, it only shows the presentation.
Yes, yes. That is nice actually. The people don't get distracted.
Yes, sir.
And I can also move.
Well, friends, so it's now 2 p.m. So I welcome you all in the first lecture of today's workshop. This lecture will be given by the distinguished scientist, respected Professor K.D. Sen. He will be talking on um, I can say he will be teaching on the introduction to density function theory. Um, so, without wasting any time, I request Professor Sen sir to deliver this lecture.
Thank you, Dr. Shukla. It's a pleasure to be part of your workshop. And as the workshops go, one has to give them the material to the extent that they don't need any prerequisite. So that is what I'm going to try now in this lecture, which is, as indicated, entitled Introduction to the Density Functional Theory. But in particular, I'll be talking about two foundational theorems proven by Hohenberg and Kohn in 1964, which are called Hohenberg-Kohan Theorem One, HK1, and Hohenberg-Kohan Theorem Two. They form the foundation of the ground state theory of electronic structure of atoms and molecules. So with that beginning, let me start by just suggesting that while quantum computational methods have two main streams starting from the early days of 1927, and I must mention here that very soon, within 5 years' time, we'll be celebrating 100 years of quantum mechanics. This particular discovery or this particular equation, the Schrodinger equation, has been the most profound achievement in science in 19th century. So we should all be very much ready to celebrate 100th year of the presentation of Schrodinger equation within a few years from now. So while wave function theory still continues to hog the limelight of many professionals in the computational sciences, we have in our plate now a very popular and useful method called the density functional theory or density functional methods, which depend upon electron density as the key parameter, as we all know by now. However, let us be very clear that it is not exclusive. They both feed on each other. They are part of our evolving knowledge database, and we have to be very attentive to each of these disciplines and their developments and see how we can sort of proceed further in an integrated way. And that is what will be actually also presented in the way that one approaches the Kohan Theorem One and Two, which is the subject matter of today's lecture. So this is the Schrodinger equation, time-dependent Schrodinger equation. So if somebody asks you to write down, for example, in an examination, what is the Schrodinger equation? So this is the Schrodinger equation, the time-dependent Schrodinger equation. The special case happens when the potential does not have any time variable in that. So you get a stationary wave equation, which is the h psi is equal to E psi. This is the eigenvalue equation, which all of us very well know. Now, this is a set of eigenvalue equation where psi is the eigenfunction of the Hamiltonian operator, which gives you a number after operation on the left-hand side as the energy, and the wave function is returned. If, however, you have any other function which is not an eigenfunction of the Hamiltonian of your n-electron system, then this equation will not be valid. You have to actually go ahead and try to improve upon that by using the variational methods. So the properties of these are very well known. They are all continuous. That means first and second derivatives exist at all values of the independent variables. There are 3n of space variables in it. The wave function is single valued because it has a physical meaning. The square of that gives you the probability of finding the electrons, and it is square integrable. That is how you calculate the probability. Then there are a couple of postulates, and the eigenvalue postulate is number 1, where you get a number small a after the eigenvalue relationship is satisfied. Then you have the expectation value. That is, if a system is in a state described by a normalized function, then average value of any observable which is given by a certain operator is given by this particular integral on the left-hand side, and that is the expectation value of the operator. That operator will be the property. So therefore, the most probable value of the property will be computed like this in quantum mechanics. Then we proceed further. If you have exact eigenvalue satisfied by the wave function, then of course this expectation value h psi will become E psi, and E is a number, you can take it out, and that will give you simply the same h psi is equal to E psi. So the expectation value becomes exactly equal to the eigenvalue if the wave function is exact, the same eigenvalue. Otherwise, if psi star is not equal to psi, then a normalized approximate wave function is not an eigenvalue, and then you use the variational principle and then minimize that. The variation principle will give you an expectation value which will be always higher than the exact energy. The lowest energy has to be then obtained by varying this particular left-hand side of the energy functional and with respect to the wave function, and you minimize this the expectation value of energy over the Hamiltonian using the approximate wave function, and scan the entire space of all possible values of the approximate wave function. That wave function which minimizes the left-hand side will give you the best possible result. It will be exactly equal to the exact result only if psi prime is equal to psi. So that is the basic introduction that we are going to borrow from the wave mechanics to develop our theorems of Hohenberg, Kohan 1 and 2. Then we have, for the present, therefore we note, as I mentioned, that this is important. The eigenvalue relationship is important. Suppose there are two Hamiltonians of two different quantum systems of entirely two different set of properties of system 1 and 2, defined by respectively h psi is equal to e psi and h prime psi prime is equal to e prime psi prime. Then of course psi prime is not an eigenfunction of h. Eigenfunction of h is a unique value of psi, in a unique function psi, and h psi is equal to e psi. Now similarly psi is not an eigenfunction of h prime, and therefore if you mismatch the pairs of Hamiltonian and the eigenfunctions, namely this is the perfect match, but if you mismatch, if you take h and do the expectation value of psi prime, then that energy will be higher than the energy of the exact eigenvalue. And similarly, if you mismatch h prime with psi, then that energy of h prime, which is exactly equal to e prime, will be much lower than the value that you obtain by mismatching h prime with psi, where psi is not an eigenfunction of h prime. So this is the basic usage of postulate 2, and this is the only thing that I will use in order to proceed and discuss the theorems 1 and 2. So here is the outline. Today's lecture will concentrate on Hohenberg-Kohan Theorem 1 and 2. So let us see how we proceed. Now, we have defined the density, electron density, we have defined yesterday also. So this is the same thing. The electron density, which is always a function of three variables in the space, is defined as rho of r, can be obtained by squaring the wave function and taking out the space and spin coordinates of all the other electrons integrated out and spin integrated out, multiplied by n. This gives you rho r, which is, so rho r dr1 will be the probability of finding the electron at any point r in a volume element dr, three-dimensional vector. And this is very, very important definition, and we will be using here afterwards the one electron density. This is the probability of finding one electron with arbitrary spin within the volume element dr1, while n-1 electrons have arbitrary positions and spin. They can be of any spin and can be anywhere in the space. So this is an experimental quantity, and this is the key parameter of the density functional theory. Now we have already discussed the theorems, the definition of function and functionals. Functional, I must repeat here, functional takes an entire function as an input and outputs a number. For example, if you have small f is a function and capital F is a functional of the function f, then if you plug in the value of the entire function in the functional f, you will get a number. And these are some of the examples. So this is the basic requirement of introduction of this particular topic. Now I will introduce the way the density functional theory has presented a different perspective of an electron system, atom, molecule, solid, biosystem, biomolecule, protein, etc., and so on, DNA and whatnot. So in DFT, the equilibrium position coordinates of the point nuclei, that is where they are located in the three-dimensional space in a molecule, for example. H2O means three nuclei, two protons and one oxygen nucleus. And where are they located? In what configuration? In what geometry? And their Coulomb attraction strength, namely what is the nuclear charge of each nuclear position. At each nuclear position, a certain Coulombic charge is sitting due to the nuclear charge, Z. And that interacts with the electrons. And this is called the external potential. Why external potential? Because we will be working within the non-relativistic framework and within the Born-Oppenheimer approximation, where electrons are moving so fast that the nuclei can be taken as fixed frozen nucleus approximation. So if that is the case, then the nuclei are external to electron interactions, because they are simply just providing a positive nuclear charge from the position of their placement in the geometry. And remember, we are talking about equilibrium geometry. We are talking about equilibrium position. And this external potential is defined as follows. So this is the electronic Hamiltonian. You have kinetic energy, you have electron-electron repulsion term, and you have got electron nuclear attraction. In Born-Oppenheimer approximation, nuclei are fixed, and therefore this will be just a point charge interaction between the nuclear charge at the nuclear position Z and the position of the electron with reference to the nuclear position. So for example, if this is a coordinate axis system, nuclei are nucleus 1, 2, 3 at capital R1, R2, R3, and the electron I is at a distance Ri. So this is how we just write down this particular interaction and sum it over all the atomic positions and sum over all the electrons. So this is how the general external potential is written down. Now, we must remember that given this external potential, that is, this potential is derived from the equilibrium geometry. Under the Born-Oppenheimer approximation, this potential is placed in the space. And if you have n electrons thrown around it, then those n electrons will adjust and distribute such that at this equilibrium geometry, the energy is minimum. Okay, and this lowest energy state in the external potential defines the Hamiltonian. Hamiltonian defines the wave function. Wave function defines all the properties through the expectation value route, because if you have wave function, you can take the operator A and calculate the most probable value of any property mathematically according to postulate 2, and that set of properties also includes the energy density. Okay, it includes energy. Now, that external potential that we wrote down as summation can be written down if you a little bit of opening up of this and taking the summation out, because this interaction is multiplicative. It only works on the position of electron 1 or electron I. Therefore, it is a multiplicative operator. It just multiplies and then gives you back the same thing and the whatever the interaction result is. So this multiplicative operator, you can take the summation out, and then this time this will be density as defined by the electron density, and therefore this entire summation can be written down as a capital V external R at a position R multiplied by the density at the position R and dr integral. Now this is an explicit functional of density. The external potential giving rise to the external potential energy contribution to the total energy is completely defined in terms of the electron density. It is a functional of density. Well, with this, we go further and write down the pictorial representation of what we are just going to do. On left hand side, I have a complete set of all one electron densities possible. Okay, these are different functions of density, function rho 1, function rho 2, function rho 3. So now I'm writing down a complete set of functions, density functions. Okay. Now on the right hand side, I'm writing down a complete set of the external potentials, which are coming out of a Hamiltonian. They are our real Hamiltonian of our n electron system, real system, fully interacting n electron system. Now we have to realize immediately that the electron density is having a unique relationship with a well-defined external potential. So there is what is called a mapping between the density and the external potential. Why? Because we have just now seen in a very, very intuitive manner that you have external potential, which is coming from the equilibrium position of the nuclei and their charges. The n electrons, total number of electrons, all giving the total electron density in the entire space around the nuclei will just adjust so as to give you minimum energy. That is the unique relationship between the one electron density and an external potential. So every density has a corresponding external potential, which is coming out of a certain corresponding Hamiltonian, which is unique. So there is a unique relationship between density, external potential, Hamiltonian, and also the wave function. Now, to be able to have a quantum theory based on density, if you want to keep these densities as the key parameters, then it is not enough to just say that, okay, given the external potential, electrons will adjust, give you the minimum energy, and therefore density is coming out as a uniquely defined thing from the external potential. But if you want to have a theory, then you have to also have the opposite mapping also valid. That is, there has to be a one-to-one mapping, that if you start with a density, there will be unique relationship, it will be connected uniquely to an unique external potential. Not just that, if you have that particular external potential, then that external potential will also take you to the density space, which is uniquely given by rho 1. So this is called the one-to-one, left and right mapping. And the mapping of the opposite direction of the arrow from what is shown here in the picture is not trivial. It is not obvious. Okay. What is not obvious is the following statement, that an external potential has a unique mapping with the electron density. Okay, we know electron density is uniquely mapped with external potential, but a given external potential has only one unique electron density associated with it, and vice versa. So this is all about what is called the Hohenberg-Kohan Theorem One. Okay, so I have given you a conceptual idea of what the theorem is all about, and we will see how it is proved. Okay, as we proceed. Now let us see that. Before we go to Theorem 1, I will give you another conceptual basis of this particular theorem. The Theorem 1 of Hohenberg-Kohan, as we shall see, simply tells us that there exists a functional of density for every property of an n-electron system in the ground state. In the ground state, if you know the ground state density exactly, then the density can be used if you know the functional of density for a given property. The functional structure is not proposed. It just tells you that there exists a functional of this kind, which depends upon the electron density of the ground state. Now, before we go to the formal discussion on Hohenberg-Kohan Theorem 1 and proceed to Theorem number 2, I want to talk about the comment that E. Bright Wilson, while he was listening to the presentation by Walter Kohn in one of the conferences, where Walter Kohn was presenting Theorem 1 and 2. This was around something around 1970-71. So Wilson argued in a conversation with some of the other participants in the conference that there exists an electron nuclear cusp condition on the wave function and therefore also on the density, which has to do with a log derivative of electron density at the coalescence point of the electron and nucleus. That is called the Kato cusp condition for the wave function, and it can be extended to the density. So let us see how Bright Wilson actually justified in the simplest possible terms what Walter Kohn was talking in terms of Hohenberg-Kohan Theorem 1 and 2. On one hand, there was rigorous mathematical foundation. On the other hand, there was a pure intuition. Okay, so this is important for us to know, because this is how we developed concepts. So you have two kinds of Coulomb interactions. One is the nuclear electron. Here is a pair of two Coulomb particles. And the pair distance is electron nuclear distance, Ri. When Ri goes to 0, when the distance of electron from the nucleus becomes 0, in the potential, you have a singularity. It becomes minus infinity. Right? Well, but Schrodinger equation tells you that at all values of R, including the coalescence point, the wave function must remain well behaved, single valued, continuous, and so on. Now, this thing is mathematically derived as a condition on the density, which is called Cato-Steiner cusp condition. At the coalescence point between the any nucleus and the reference electron located at position I from the nucleus, if you take the log derivative, the bracket term is logarithm derivative of log of rho r with respect to r. If you take this log derivative of r and move the electron nuclear distance to 0, that is at the point of coalescence, this term is exactly equal to minus 2z. I must mention on the sideline here that this cusp condition is valid for all electronic states of all n-electron systems, ground state as well as excited states. But we will be concerning, we will discuss in particular the ground state. Now, this is what Wilson remarked. He said that, well, if electron density can define all the properties, here it is why we already know. He said that electron density rho contains the information on where the nuclei are located. Because if you take electron density and take the derivative like this and go on changing r, you will reach a position where in the space, this particular left-hand side from the density will give exactly a value of minus 2z, a constant value. And you know that the nucleus is sitting there at that position. In addition to the knowledge about the position, it also has the information, the electron density also has the information on the nuclear charge, the Z. Okay, for hydrogen it will be 1, for helium it will be 2, and so on, which means that electron density has the electron density of the ground state of the n-electron system in its equilibrium position has the information on the location of the nuclei as well as the identity of the nuclei. Therefore, the external potential is completely defined by the density. Okay. This is how he argued. And then it was like very simple, things very much simplified. But then there are certain very subtle things which we will learn as we take up the mathematical derivation of these theorems. What are the advantages in the light of discussion so far? The advantages are in terms of the following questions for 1 and 2. Well, first, mainly question 1. Is it possible to describe the electronic structure exclusively in terms of electron density? The answer is yes for the ground state at this time. And what will be the advantages of this? The main advantage is that we bypass the use of Schrodinger equation. Okay, we don't have to use Schrodinger equation. We used to use some other equations, which we will see. Then it reduces the handling of 3n space variable of wave function psi, 3 for each particle, n for n number of electrons, to just 3, merely 3 variables. And alternatively in chemical sciences, rho, and in physics, n of r are used for connotation for the density, 1 electron density. It has been very used for chemists, material sciences, biochemists, and so on. Physicists, handling with materials. And the advantage is that you can do very reliable calculations including 1,000 atoms now. While in the wave functions, you cannot go beyond, let's say, 10 atoms in general with the reliable results, which give you the accuracy of, let's say, chemical accuracy of a 1 kilocalorie per mole. So this is the advantage. Well, now we start. Now from here, the formal discussion on Hohenberg-Kohan Theorem One starts. Before we actually touch the Theorem One, after 3 or 4 slides, I want to recapitulate whatever I have said in terms of mathematical notations, because every mathematical notation has a very useful meaning and significance, physical meaning, which we already discussed. Now we will just put them down, let's say in kind of a shorthand notation of mathematics. Okay, right. So let us start very simply. Simply we begin with 2 electronic systems with same number of electrons, and they have the same parts in the total energy description of kinetic energy and electron-electron interaction energy parts. We will see what do we mean by the part, the Hamiltonian part, the operator parts. So therefore, if you write H of that electron system and write down the Schrodinger equation, stationary Schrodinger equation, He will be kinetic energy operator, electron-electron repulsion operator, and the external potential that we have seen. Now, as I told you, that external potential is what is the key which defines the Hamiltonian. This and this will be outcome of the n electrons distributing around the external potential to give you minimum energy, right? And therefore, the external potential distinguishes the Hamiltonian. For 2 different Hamiltonians, H and H prime, there will be 2 different external potentials, which is very clear from the definition. We will consider only the non-degenerate ground state. But I must mention here that all that we prove in the entire lecture today can be extended easily to the degenerate states as well. But we will assume that there is only one electronic state in the ground state energy. So what we do is the following. Now we are now preparing our ground rules of how we will actually look at our n electron system in the density functional theory. And I will give you the simplest possible presentation. Collect all such ground state wave functions into a set psi. So capital Psi is a set of all the ground state wave functions. Okay, all the ground state wave functions. There will be so many Hamiltonians. Corresponding to that, there will be so many ground states, and so all those ground states of an electron system are put down together. So the set will have elements. Set of psi in bold letters will have elements of psi, that is wave function psi, given by this particular symbol, and this n electron wave function will be different elements, and there will be each element, each psi will be associated with one external potential and one Hamiltonian. One external potential which is determined by the Hamiltonian, right? As I already indicated. Now, there exists one-to-one mapping. Mapping will be called C. There is a mapping called C, which is telling you that it includes that any element in the external potential set will map exactly uniquely onto the set of the ground state wave functions. So if you have V1, if this is the set of external potentials, this is a set of ground state wave functions. Each external potential corresponding to Hamiltonian H1, V2 corresponding to H2, V3 corresponding to H3 will exactly identify and fall into psi1, psi2 and psi3 respectively. Okay, right? Now let us see how this is so. Please pay your attention to these equations. They are very simple to understand if you follow what is written there and the description that I am going to give you. Let there be 2 external potentials. Let there be 2 elements of V, of the set V, external potential set, such that they are not the same, such that one is not related to the other simply by a mere constant. This is not different, okay? Because you know, in all experimental things, we'll take the differences of energy. We measure differences of energy, and therefore, if you have any constant in between, that cancels out. So therefore, there is no change, and therefore, one external potential will be really different from another external potential if and only if it is differing from the other external potential by more than a constant, something more than constant. Okay, so this is important. So this difference is not a constant of two external potentials. Now let these two be the elements corresponding to the associated ground state wave functions. Psi 0 is associated with VEN and psi 0 prime is associated with VEN prime. Prime with this prime and unprime with this particular unprime, associated with two different external potentials. So we write the two corresponding equations. H psi 0 is E0 psi 0, one Schrodinger equation. H prime psi prime is equal to E0 prime psi prime. Okay, two different Schrodinger equations. H psi 0, H prime psi 0 prime, giving you energy E0 and E0 prime. The very first equation that I wrote down, eigenvalue relationship, eigenfunction relationship. Now we will show that if we assume that these two wave functions are the same, if we assume that the two wave functions corresponding to two different external potentials are same, then we get a contradiction. This kind of method of proof is called the reductio ad absurdum. You assume something and see to it that that assumption leads you to the absurd results, which actually tells you that mathematically that assumption must be wrong. Okay, so we will assume that the two wave functions corresponding to two different external potentials coming from two different Hamiltonians are the same. If you do that and subtract this from there, because this and this, TE and VE are constant, they are the same for both the equations, they cancel out and we will have here the difference. So difference between two Hamiltonians is essentially the difference between two external potentials, because that's the defining parameter, that's the defining function of the Hamiltonian. So left hand side gives you this, you take 2 minus 1, you get left hand side this, and right hand side gives you this. Remember, these two are E0 and E0 prime are numbers. Okay, and now this equation is very easy to simplify because you have these operators, they are multiplicative operators, they are just functions of R, so that they multiply and give you something else which is returning the number and the function. So if that is the case, if they are the numbers, then you can write down that this particular left hand part must be equal to this part.
Hello?
But this is not what we started to begin with.
It's good, like quantum theory.
So the difference between two external potential is not a constant. This result, which is absurd, that the difference between two external potentials of two different Hamiltonians is a constant, is not what we started with. It is not equal to a constant. VEN is not equal to VEN prime plus constant. Whereas this is telling you that this difference is a constant. Therefore, this particular original assumption that the two wave functions corresponding to two different external potentials can be the same is wrong. And this proves, therefore, the first mapping, that each external potential must give a unique wave function, ground state wave function, subject to the requirement that one external potential differs from the other external potential by more than just a constant. That's very important. By more than merely a constant. Okay, this merely a constant thing has to be kept in our background of discussion. Now, I will now take up to discuss the opposite mapping. That is to say, from the mapping from here to here we have seen just now by assuming something which was absurd. Now we will take the mapping from this to this side. Wave function to this mapping, and this is not trivial, but we'll see how it goes. So inverse map. So C becomes C inverse, right? And mapping has to be from the wave function set. So mapping has to be from this side. Earlier on it was from right to left. Now left to right. Now it is from right to left. We are mapping wave function to its unique external potential. We are mapping wave function to its unique multiplier, and so on and so forth. Remember, we are discussing wave function, not density. We are discussing wave function and trying to actually see what we already know from the wave functional theory from 27 to 64. Okay, so this is what we will do to actually prove the inverse mapping. Okay, inverse mapping, again, to be specific, I must tell you that it is C external potential to wave function set, and now it is C inverse wave function to external potential set. Okay, now we already have seen that two different wave functions will be corresponding to two different external potential. Now let us assume that the two external potentials are the same. Okay, corresponding to two different external potentials, giving you two different wave functions. Let's assume that what happens when they are the same. So we write the Schrodinger equation the same way as we wrote before, right? But now, what does it tell you? It tells you again something very absurd. That is to say that, look, here is the Hamiltonian. Here also it becomes the same Hamiltonian because the two external potentials become the same. That means the absurd result is that this Schrodinger equation is telling you that this is the eigenvalue equation. This Schrodinger equation is telling you that this is the eigenvalue equation for the same Hamiltonian, which is absurd. It can be either this or this, and we know that H psi 0 is E0 psi 0, and therefore this particular thing has to be equal to psi 0. This psi 0 prime has to be equal to psi 0. So therefore this particular statement gives you that psi 0 prime cannot be the ground state of the Hamiltonian, which is the same in both the cases because we are assuming the two external potentials the same, but it must be a ground state of H prime, this particular Hamiltonian, which is equal to the original Hamiltonian. And therefore, this is a contradiction, and so this contradiction will not be allowing us to assume that this can be true, right? So therefore, we have now mapped the elements of the wave function to the elements of the external potential. So each wave function, if the two wave functions are different, then they will map exactly corresponding to their unique external potentials. So we will go from now right to left. This will go here, this will go here, this will go here. This is inverse mapping. So direct mapping and inverse mapping together is known as one-to-one mapping, and we have now mapped the wave function and external potential. Now this in the quantum mechanics lingo will be stated as follows, that the external potential defines the Hamiltonian, the Hamiltonian defines the wave function defines all the properties of the electron system, including energy, right? The same thing can be written down again in terms of the wave function defines the external ground state wave function defines a unique ground state external potential coming from the ground state Hamiltonian, which defines all the properties of the system. Okay, now with this background, so we have now given, I will conclude in one sentence. We now know that there is a unique mapping between wave function and external potential, and therefore the Hamiltonian defined by external potential defined by the wave function defined by the external potential defining the wave function, right? This is what we know. This is what the simple Schrodinger equation is telling us about. Now we will move to we will now use this result, we will now use this particular knowledge and try to discuss the Hohenberg-Kohn theorem. Now we come to the density, because Hohenberg-Kohn theorem or density functional theory is all about the density of the ground state of the n electronic system. The wave function integrates to n, the density integrates to n, and they are both coming out, they are both arising from a Hamiltonian. They are both, the wave function and the density are arising from a particular external potential. Such densities are called V for external potential. Such densities are called V representable densities. V representable densities. These densities are representable in a certain external potential, defining a certain unique Hamiltonian, defining a certain unique ground state wave function. Okay, so this is how we start now. And we'll go back to the same definition, starting with the density. And now we construct two different sets. Okay, one set is we have already discussed. One set is all the ground state wave functions of different Hamiltonians of the different ground states. Okay, then we have corresponding wave functions giving us densities, and therefore now we have a new set of densities, new elements in this particular set. We'll call it as some kind of a slanted, italicized capital N. Okay, N for density, let's say. So we have now two sets. One set is the same wave functional set, ground state wave functional set, and one is the corresponding ground state density set. Okay. One mapping from ground state density, ground state from left, from ground state wave function to the ground state density will be D. And the inverse mapping will be from right to left, that is from ground state densities to the ground state wave function. Let there be n number of several ground state densities and several ground state wave functions. They must correspond to each other in one-to-one uniquely. Okay. This particular thing is the basis of the density functional theory, as we have seen in the previous discussions of 2 or 3 slides, as the basis of the Schrodinger theory between the one-to-one correspondence between the ground state wave function and the external potential. Now we are talking about the correspondence between the ground state wave function, which defines the external potential from our previous discussion, to the densities. So we will take the left mapping first. Is this true? Does a ground state wave function define the ground state density? Does it exist uniquely? Yes, of course. This equation 1 is telling you that. This is how you have defined the ground state density coming from the ground state wave function. Right? So therefore, equation 1 is trivially telling you that this kind of relationship must exist. There must be a one-to-one, there must be a left to right mapping between the ground state wave function and ground state densities in the two sets. But the opposite, the inverse mapping, is less trivial. It's not easy. Okay. That is the mapping which means that the density uniquely defines the wave function is not clear. Right? Because once that is clear, then uniquely defined wave function will uniquely define the external potential, and external potential will uniquely define the Hamiltonian, and then all the properties will be calculated from the density alone. So we have to now see or show that this is true, that the density uniquely determines the external potential. So this is what we will now prove the next, and that's Hohenberg-Kohan Theorem One. Okay, we'll first prove it, and then we will discuss its implications, its physical meaning and its implications in physical sciences in general. So we first define our n-electron system in an external potential which completely fixes the Hamiltonian, and the n-electron system will be always such that the integral of the density normalized or the wave function normalized will be n, and the external potential will determine all the properties, right, for the n-electron system from the simple external potential point of view, from the wave functional point of view. Now Hohenberg and Kohan proved this theorem, which I will state first. the external potential is determined. So this is now the inverse mapping to within a trivial additive constant. It's the same constant when one external potential has to be different from the other external potential by more than a constant. So if there is only a difference of constant, then it doesn't matter. It will be the same thing, saying the same thing. So the external potential is determined by electron density. So if you know electron density, then you can determine the wave function, ground state wave function, and therefore from the previous discussion, you can determine uniquely the external potential. If you know this, then you can uniquely go there, right? From the Schrodinger theory that we learned. So therefore, now we will try to prove this theorem 1 in the simplest possible manner from whatever we have discussed today. You don't need any other information. So suppose the proof goes as follows. Suppose there are two external potentials, V and V prime, differing by more than a constant, because that is our definition of being two different external potential. Each give you the same density. Suppose we assume this for its ground state, right? Each give you the same density. So V will define one Hamiltonian H, V prime will define another Hamiltonian H prime. They both give the same density, but their wave functions are different because you are two different Hamiltonians. Suppose we assume this, then let's see what happens. Okay, so we know that H goes with psi, gives you E0, and H prime goes with psi 0 prime, gives you E0 prime. That is the eigenvalue relationship. If you mismatch, then the energy will be higher than the exact energy. So what we do is we take the Hamiltonian H, whose exact energy is E0 when the eigenvalue is psi. But if it is mismatched with the expectation value of psi prime not being the eigenfunction of psi prime is not the eigenfunction of H, it is eigenfunction of H prime. So if it is not an eigenfunction of H, this expectation value will be higher than the eigenvalue of H, which is H psi is equal to E0 psi, variational theory, right? If this is starting point, then this portion in the second part can be written down, can be expanded as you write H as H prime minus H prime plus H. Sorry, you write H as H prime plus H minus H prime. So H prime and H prime are subtracted, leaving behind H. So you are writing H as H prime and H minus H prime. This minus H prime will cancel out this term, and you will be left with H prime H psi prime, which is this. Now, if you proceed from here, you see psi prime is an eigenfunction of H prime with the eigenvalue E0 prime. And therefore, this completely gives you this particular eigenvalue, because now this expectation value is equal to the exact eigenvalue, because there is a perfect pairing, perfect match between it's an eigenvalue equation. H prime psi prime is equal to E0 prime psi prime. And psi prime E0 can be pulled out being a number, and the integral will be 1. Psi prime will be 1. Now, this portion is nothing but the expectation value of difference of the two Hamiltonians with two external potential. And we have seen already by the definition of the external potential that the difference between two Hamiltonians is just the difference between the two external potentials. So therefore, we write this directly, this for this and this for this corresponding external potential, and this is our equation 1. In the next similar part, what we do is we mismatch H prime with psi. H prime has the eigenvalue as E0 prime. And if you mismatch this with psi, then this particular integral will be always higher than E0 prime. And this is what we do next and get exactly the same result. So we are mismatching the H prime with psi. Psi is not an eigenvalue of H prime, it is eigenvalue of H. And therefore, the expectation value of psi will be an approximate function only for H prime, and the expectation value will be higher than the eigenvalue of H prime psi prime is equal to E0 prime psi prime. Now you open H prime as H plus H prime minus H. So minus H and plus H go away, leaving behind H prime, which is the same thing as this one. So these two are equivalent. Now H and psi are eigenvalue eigenfunction relationships. So therefore, h psi will give you E0 psi, and psi will be out in the integral, and E0 will be out. So you have E0 here corresponding to the eigenvalue of h and psi, and this difference will be written down in this particular form. Now this is unprime and prime here, and in the previous one we have unprime and prime here, but there's a minus sign here in between, and there is a minus sign here, and there is an opposite plus sign here. There is a plus and there is a minus here. Okay, so therefore equation 1 and 2 have this particular term of opposite side. Just to add the two, left hand side will be E0 prime plus E0 from the previous one. Right hand side will be again E0 prime and E0 from the two previous equations. And this cancels exactly with this part, equation 1. Second term of equation 1 and 2 cancel out. So this is what is the result we get, which is absurd again. That means our assumption that the two different Hamiltonians with two different wave functions will give you the same density is wrong. It must be that two different Hamiltonians defined by two different external potentials must give you two different wave functions corresponding to two different densities. So this is what is the inverse mapping that we have shown. That is that you have this particular result, that you cannot have a density same corresponding to two different external potential correspondingly. Therefore, you have to have a given density directly and uniquely related to a given ground state wave function, which is related directly to the ground state Hamiltonian and the corresponding external potential. So this is the inverse mapping, which is proven by Hohenberg-Kohan Theorem 1. Now this is what is the meaning of the Hohenberg-Kohan theorem. That is that density defines uniquely the external potential. External potential uniquely defines the Hamiltonian. Hamiltonian uniquely defines the wave function, and therefore all properties, including the energy, can be also determined by the density. In the previous discussion of the mapping between the wave function and external potential of the Schrodinger theory, we did the same thing, starting with wave function is uniquely determining the external potential. External potential is uniquely determining the Hamiltonian. Hamiltonian determines all the properties, including energy. Now we are able to say the same thing for the ground state. And why ground state? Because we are doing the minimum energy of the expectation value, the eigenvalue minimum. Okay, we'll see this a little more later on. But then the final result of all these discussion is the following, that the electron density determines all the properties, including energy. And we say this, including the energy, and taking the example of energy, we say that energy is a functional of density. Indeed, in the most general terms, every property is a functional of density in the ground state. And in particular, the ground state energy is a functional of the ground state density. Okay, so this is an existence theorem. Okay, it says that such a theorem exists. It is mathematically rigorous, it is exact. Okay, now this is the representation for energy. Energy density functional at a given external potential will be given by the kinetic energy density functional, the electron nuclear or the external potential density functional, and the electron density functional. All three parts are exactly determined by the density alone. Now we rewrite this partition, keeping in mind that it is the external potential which is actually defining the Hamiltonian, and also the minimum ground state energy. Therefore, this external potential part can be written down in this fashion, along with the external potential and the density. This is the functional part of the energy partition of the external potential. And the two other things are written down as a functional which is called the Hohenberg-Kohan functional FHK of rho, which is equal to T of rho and VEE of rho. So essentially what this step is doing is that it is just simply telling that, look, in the energy density functional, we know the external part, which is the density functional, which is given by this, because it's a simply multiplicative one electron part with the density, exact density, okay, which uniquely defines the Hamiltonian and all the properties. The other part of the functional is just a universal functional, which is adding on depending upon how one external potential differs from another external potential. Now, this is very important. This is a very, very significant step, though written down in a very trivial fashion. It is telling you that the energy density functional exists. That is point number one. Second is that it exists. Its total complete form is not known. It is unknown. And in it, in the unknown part, if we just move our hand around, we will find that there exists a universal functional which is the same for all external potential, which is the same for all n-electron systems. This is really very far-fetched, because if by some good luck we happen to know this FHK for just one n-electron system, suppose we know this for hydrogen molecule, then this functional will be the same, exactly the same for any molecule under the sun. Okay, that is for the ground state, of course. That is what this particular theorem 1 means. Okay, so what is further done according to this particular theorem, which is the existence theorem? It does not tell you what exactly this is formally, but it tells you what are the features of this. There is an universal Hohenberg-Kohan functional of energy. And in addition to that, if you add the external potential, which is actually a distinguishing feature of one system with another one, two different systems have two different external potentials. Okay, and this will be therefore the construction of the energy density functional in the Hohenberg-Kohan theorem 1. And this FHK is again this plus this, and the electron-electron interaction can be further partitioned into the classical Coulomb term and the non-classical terms, which are quantum mechanical terms, which are exchange and anything else, which we will see later on. Okay, so therefore this is the partitioning. Now with this in mind, let's see what are the useful insights of Hohenberg-Kohan theorem 1. Although we are having proven the exact mathematical results, first, it is an existence theorem. It proves that there exists a function of density for all ground state properties, including energy. And this is the partition, as we have just now seen. And the electronic interaction functional of contributing the energy is written down as the Coulomb part of the functional of density and the exchange correlation part of the functional of density, which is the non-classical interaction. And here is the last, not often recognized virtue of theorem 1. And this has been the mainstream of all the modern developments in the last 10 years in the density functional constructions, which work to the chemical accuracy in the ladder 4 or even 5 of the Yakov ladder of the functionals. And that is the following. Please pay attention to this because it's very important. This is that HK theorem 1 holds good for not just VEE of fully interacting system that we have been discussing so far. In our Hamiltonian, we took this as fully electronic interaction system of pairwise electrons, the real interacting system. It holds good for a constant lambda times the interactive. If you put VEE by lambda times VEE, where lambda is anything between 0 and 1. Anything between 0 and 1 means when lambda is equal to 0, there is no electron-electron interaction. Such a fictitious system is called the non-interacting system. So it is valid for non-interacting system to any strength of the interaction until the final fully interacting system where lambda is equal to 1. When this is 1, we have the fully interacting system. We have the normal Schrodinger equation, we have normal Hamiltonian for the n electron system. So lambda is equal to 0 defines a non-interacting system. Lambda is equal to 1 defines the fully interacting system. There are some wonderful concepts emerging out of this, and one of them is the adiabatic connection method, right? You can change the interaction from lambda going from 0 to 1 and integrate over the quantities to get some beautiful identities, which we will see later on. So therefore, the Heisenberg-Cohen theorem 1 focuses on unique density corresponding to the exact ground state. And once you know that, all properties are in principle determinable. The problem is that we don't know the form of the functionals corresponding to those properties, including energy. Right. Now we go to the part, in the remaining part of this lecture, I will discuss the Heisenberg-Cohen theorem 2. Now, remember, in all our discussion, we have been explicitly emphasizing the fact that the ground state density is arising out of a certain external potential which is defining the Hamiltonian. And such densities are called the V representable densities, external potential representable densities, right? Now, these densities are all integrated to n, and they are coming from a certain Hamiltonian with a certain specific external potential. How did we calculate the density? Density is calculated always by in terms of certain integral. Okay, this is how we calculate densities from the wave function. So we take a function, let's say in general, we generalize this thing as a function. We take square of some function and integrate over certain variables. And numerically, they are called numerical quadrature. The right hand side is a quadrature. From some lower value to the upper value of the variables, we integrate numerically. Now, this psi here is coming from a V external potential. So therefore, this V representable density is coming from this wave function, which is associated with a Hamiltonian. But it is not necessary that we get this density function only by this function. There can be many other functions which, when square integrated, will give you the same function. Okay, right? So therefore, you have something, there is a set of V representable densities, but there is a larger set of densities which includes densities in addition to V representable densities. Requirement on these densities is that they are normalized to n. So a general set of densities obtained by this kind of an integration by any function here, including the wave function corresponding to the ground state, will be called as a larger space of the wave functional space. All wave functions are coming from the external potential, but here all densities are normalized to n. Wave function plus any other function can be integrated to give the same density. Okay, or a set of densities, a general set of densities. Why are we talking about this? Because we have to now look at Heisenberg-Cohen theorem 2. And at the end of Kohan Theorem 2, we'll come back to this requirement that we discussed now of V representable densities. Okay. So Heisenberg-Cohen Theorem 2. First, let us discuss this. And I'll come back to what I just now said about the V representable densities. V representable density is a subspace of a larger set of densities which are not necessarily coming from any Hamiltonian, but there are functions which are giving you the densities. Okay, there are functions which are giving you the densities which are normalized to n. So in the larger set of requirement, we have the requirement that the density is integrated to n. They need not come from any external potential. Such larger set of space of density functions are known as capital N representable densities. So n representable densities are all normalized to 1, are n representable densities. They are the larger space of the density functions. Then a smaller space or subspace of the function of this larger space, which is V representable densities. Here, all the densities are coming from certain Hamiltonian and external potential and the wave function, right? So this is our background. The background as is applicable to our theorems 1 and 2 is that our theorem 1 and 2 are valid only and only on V representable densities. We have all the times a Hamiltonian there and an external potential there. Remember that. Okay. Now, Kohan Theorem 2. Let us state it. Actually, this theorem tells us that this is the statement of the theorem, the last line here, that if you have exact density and you plug that exact density into the energy density functional of what is given by Cohan Theorem 1, the existence functional, then you will get the exact energy which is given on the right hand side. But if you take that functional EV and instead of rho, which is the exact density, ground state density, you plug in any other density which is normalized to n and coming out from a certain external potential and Hamiltonian, then that energy coming out from the energy density function will be always higher than that obtained from plugging in the exact density into the functional. So energy density with exact ground state density will always give you the lowest energy. Any other density will give you always the energy which is higher. Now this is something similar to the variational principle, including the wave functions in the ground state. And this is why the two theorems are actually constrained to be applicable to the ground state per se. Okay. Now we'll state theorem 2 as the minimum energy of the functional will be obtained by that condition which minimizes the functional variation with respect to density to its minimum. Just like we did the wave functional energy expression and minimize that energy with respect to wave function, we can do the same thing. Here we take the energy density functional, take the derivative of that with respect to density, and the minimum one will be the best value of energy that we can obtain. Remember, in the wave function variational minimization, we had a Lagrange multiplier which was introduced in order to make sure that as you vary the wave function, the requirement of the normalization does not change. Because you cannot change your system given to you. An electron will have to be an electron if you change the wave function. If you make it psi to psi plus delta psi at one place, then it has to be compensated as psi minus delta psi elsewhere, so that the total normalization remains the n constant. Same thing here. When you vary the density from rho to rho plus d rho, then you cannot get out of the normalization requirement that the total number of electrons must integrate to n. So your density, new varied density has to also normalize to be n. So that is achieved mathematically by what is called the method of Lagrange multipliers, which is what we will do next. But now let me just try to give the statement of Cohan Theorem 2. For any trial density rho prime r such that rho prime r is larger than 0, is all positive, and it is integrated to n always. So this is the requirement of normalization as you vary, right? Then energy obtained by the trial density will be always above, which will always higher than the exact energy that is obtained by the exact density. So exact density put in the energy functional giving you the energy is the lower bound. From below it binds all the other possible energies when you plug in all the other approximate densities. Equality holds only if and only if the two densities are the same. Okay. Now, with this statement, we will now prove this theorem too. It is actually a high school algebra. All right. So far we have seen this one-to-one correspondence. Density has one-to-one mapping with the external potential. External potential has one-to-one mapping with the Hamiltonian. Hamiltonian has one-to-one mapping with the wave function, and vice versa. Okay. So you can either, for the ground state, what you can achieve from Schrodinger theory, you can achieve for the ground state from the density functional theory based on the Cohen Theorem 1 and 2. So energy density functional given by Cohen Theorem 1 is of this kind, FHK and the integral of external potential of rho. Now we take another density, rho prime, coming from another external potential, coming from another Hamiltonian, coming from another wave function, and write the functional now not in terms of rho, but in terms of rho prime, not in terms of v, in terms of v prime, and so on. So exactly this will be replaced by the corresponding terms here, and you will get this result. So FHK plus this, FHK plus this. This is rho prime. There is a prime here. Rho prime. This is rho prime. Okay. Now let us use rho prime as trial density of H. Okay. We are using rho prime as trial density of H. So we are mismatching this. Okay. We are. So rho prime is coming from psi prime. And instead of working with H prime, where psi prime and rho prime were directly coming out, we are now mismatching that with H. Right? Now this, according to the variational principle of wave mechanics, quantum mechanics, or wave functional theory, H and psi prime are not the eigenfunction eigenvalue relationships. H and psi are. So if H and psi is there, which is the exact eigenfunction of this Hamiltonian, then this expectation value of the wave function, according to postulate 2 of quantum mechanics, will be always lower than this. Okay, because H is now mismatched with psi prime, whereas the actual value is psi. So therefore, this expectation value of the operator will be higher. Now, we write this particular left-hand side, this piece here, we expand it. H psi prime, we expand. So psi prime will give you rho prime, and FHK will give you rho prime, and we will get what is known as E rho functional when rho prime is substituted, because this is nothing but that particular definition. The energy density function of HK theorem 1 is this with rho and this with rho, and we put rho to rho prime. This will give you the energy density functional as is obtained by the number when you put the rho prime as the density function, right? And this part will be always higher than this, and this portion is nothing but, according to the lowest ground state energy, exact energy, this is the Cohen Theorem 1 minimum energy, the ground state exact energy. So the exact energy of the ground state obtained by the functional by substituting the exact density is always going to be lower than the energy that you obtain by substituting any other density which is not exact density, right? So the variational principle of wave function is now recast in terms of the variation of energy density functional with respect to density in the ground state, right? Now, if this is the case, then earlier on we had psi here in the wave functional theory, and we could minimize this functional subject to the constant of the normalization of the wave function and get the minimum wave function corresponding to the variation theory. The same thing we will do for the density. We take the energy density functional, we vary that with respect to density, but we put a certain Lagrange multiplier mu, and in the bracket we put the constant that you cannot vary density arbitrarily. You have to always vary in such a manner that the density integral is always equal to n. And this particular red part during the variation ensures that as you vary rho in this variation of the energy density functional with respect to density, the constraint of the n normalization is always held. Okay. Now we take this energy density function and write down in terms of the Kohan Theorem One, external part, and this FHK, and then this particular thing, and we have taken the we take the derivative of the, of course there is an integral here, there is an integral sign missing here, there is an integral there. So now we take the derivative with respect to rho. If you take the derivative of this part 1 with respect to rho, this rho will go away because it is derivative with respect to rho. So like d of x by dx, it will be 1. So you have this VR coming out. You take the derivative of this, you get the functional derivative of the Hohenberg-Kohn universal functional with respect to density, and this rho will give you 1 and mu will come out with minus sign, and this is a number. So the number with respect to any variation will be 0, and therefore this is your variational equation of the density functional theory, which is coming out from the Hohenberg-Kohn Theorem 2, which tells you that you can use the variation of density in the energy density functional with respect to density, and the minimum of that given by the density will give you the best value of the energy as well as the density. So therefore, this equation 3, we will rewrite this. We'll take this number on this side, it's just a constant. So you have mu, and mu on one side, an external potential, and the functional derivative of the unknown universal Hohenberg-Kohn functional is equation 4. This is the key result of Hohenberg-Kohn Theorem 2, right? So this is where one should just conclude this and make some special comments about what we have done so far. If we know exact Hohenberg-Kohn universal functional, then Hohenberg-Kohn theorems 1 and 2 guarantee that exact ground state energies of a given system can be used to obtain all the energies, including all the properties, including energy. Now, this universal functional is defined independently of the external potential. So therefore, this is a universal functional. For a given external potential, the density will change, and then this functional will change to give you different energy. Remember, because this is important. This is the functional. There is an integral here. This is the functional. Okay. So now, if that is the case, then it is important to realize, it is important to emphasize, and this is how all the activities began after 1964 when these theorems were given. It is important to emphasize that the existence of an exact theory such as HK Theorem 1 and 2 provides impetus both to work to advance the calculational procedures or computational methods to higher accuracy, and also to strive to develop the conceptual consequences, because there exists something which is exactly known, right? So in fact, if you recall the wave functional theory, the only exact thing that we knew there was the solution of the hydrogen atom, the hydrogen orbitals, 1s, 2s, and then we developed so much as atomic orbitals, molecular orbitals, and so on and so forth with that. Now, as we have already indicated earlier on, the final comment is that it is the HK Theorem 1 and 2 give you a reformulation of the Schrodinger wave mechanics in terms of the density, as we have already noted, and it is written down here. This part, the mapping. Instead of working with this, you can work with this for the ground state. That is what it means. So, to conclude, the Theorem 1 and 2 of Hohenberg and Kohn, given in 1964, introduced two new things into the vocabulary of the two basic key parameters in terms of new expressions into the vocabulary of density functional theory. One is the universal HK functional and the external potential. It is the external potential which is a controlling button. Okay. And now I will conclude here by making this observation which I mentioned earlier on, that if you have to do this variation, if you have to do this variation, if you have to satisfy this equation to get the best value of energy and the best value of density, exact density you may not know, then you have to vary with respect to density. This variation is with respect to density. Now, which densities? Because theorem 1 and 2 are valid only and only if the densities are V representable. And you have infinite other densities which are not V representable. There are infinite functions which will be integrating to give you a function which integrates to 1 or which integrates to n. But those densities or those functions may have nothing to do with Schrodinger equation or Hamiltonian or external potential or even an electron system. They may be somewhere coming from some other systems, right? Therefore, how do you pick and choose your variational space? How are you sure that you are going to vary only with V representable densities? There is no way. Because there is nothing that mathematically defines a V representable density. There is a general space of n representable densities which include V representable densities as well as a whole lot of other densities which are not V representable, but they all integrate to n like V representable density. So you have a problem here. A, you have to vary with respect to V representable densities, and you do not know what V representable densities really are because you have no way to mathematically define and pick and choose the variational machinery by varying with respect to the V representable densities. Okay. So this problem existed because the conditions for a density to be representable, V representable are non-known. However, on the other hand, the wider space of n representable densities, okay, can be mathematically defined. Okay. And those definitions are the following. A n representable density, a density is n representable if it is everywhere positive, if it is integrated to n, and if the gradient of the square root of density square integrated over the space is less than it is not infinite. It should be finite. These conditions are the conditions for the n representable densities. Now I will conclude here and take it up from here in the next lecture. So it would be very nice to be able to expand and generalize the Hohenberg-Kohan Theorem 2 of variation not just with respect to the n, not just with respect to the V representable densities, but n representable densities, so that you can take any density and go on varying. Okay. So this is what was mathematically proved by the time when he was proving these theorems. He was in New Orleans, and these two people actually generalized the variational step of the density functionals of energy to any arbitrary density which is just integrated to n and which only satisfies this requirement. And therefore, the scope of this was widened and it could be applied for any density. You could start with any density and start the minimization. It is not just that it was not being done. When 64 the theorems came, people already were trying to minimize with respect to density, but they did not know that this can also be done in principle. which was actually proved by, it was a mathematical problem. It was a big challenge before the density functional theories of between 64 to 79 until it was solved by these two people. Okay, so here I will conclude the lecture today, and in the next lecture I will start from here, and I'll follow that up. After generalizing it, I'll follow it up with the Kohan model. Okay, so I will conclude here by just stating that we are dealing with exact theory. Theory is exact at this point, and we must be able to realize that whatever approximations we'll do, we will see it later on. So thank you very much. If there are any questions, I will be happy to answer.
Yeah, thank you, sir. So participants are now the line open for questions. If you have any question, please unmute yourself and ask.
Yeah.
Dr. Coulomb
Yes.
has asked.
Yeah. Sir, it was a very nice presentation actually. Although I am involved in the field of DFT for the last 15 to 16 years, but still the basic knowledge coming from your lecture is again a refreshing one. So I have a query. We deal with different systems of different sizes with DFT. And as we know that HK theorem is the basis of the calculations, because next you are going to talk about the Coulomb equations. So question is that since we have learned that ground state density will basically be required to know the ground state energy and which will be the minimum, because any other density will lead to energy greater than the ground state energy. So the question is there any limit on that delta E value, means delta rho value? Is there any limit on that if we consider any other density, which is not the true ground state density, then we may encounter any other energy which may not be the ground state energy?
That's
so
correct. Yeah.
So
please finish your question. Have you finished your question?
Because we are...
Hello?
Yes.
Okay, can you hear me?
Yes.
Yeah, okay.
Yeah, I can.
Yeah. So it is your question is a very general one. It is true for any variational ansatz. So whenever you are varying, if your initial guess value of your guess function, let's say wave function or density, if it is close to the exact wave function or exact density, then you will be converging very fast. Otherwise, you will start with a very, very distant kind of a point, and then you will take in the cycle of iterations in the formalism which actually implements these theorems in practice. In wave functional theory, you have LCAO, and you take the C1, C2, C3, all variational parameters, and then minimize that. In the density functionals, you will have the Coulomb equations. There again, you will have a basis set for the Coulomb orbitals, and you will minimize with respect to the basis of the Coulomb orbitals. So therefore, the densities corresponding to that Coulomb orbitals, if there are starting density or the guess densities, if they are too much off from the exact densities, then you will have definitely a very crude estimate of the energy. Okay, so closer.
But sir, yes, the question was that if we start with some other density, which is not exactly the true ground state density, but little bit off from the ground state.
Yes.
But in that situation, there is also a probability that we may trap in some local minima.
Yeah, so that is how it is done in practice. You have these the minimum of the surface is obtained by several methods, the steepest descent methods and things like that. So if you are close to that minimum point, then you can reach the minimum by a variety of numerical techniques, which are very well known now. Okay, so any variational like gradients, you map the gradients, you map the second gradient and things like that. So if you are close to the minimum, that means if you start with the exact energy with exact density plus a certain delta rho, which is very close to it, then you have very well-defined mathematical iterative methods to go to the minimum.
Yeah, so sir, regarding the practical calculations, when we carry out our calculations say, using some software like Gaussian or maybe quantum spacer, so there we have to make sure that we are reaching the true ground state. So will there be some separate calculations to confirm that?
No. The minimization with respect to the variables is very well programmed in the commercial course, such as Gaussian or games and so on and so forth. So that is how you actually reach the minimum. Is what? The minimum is something like a numerical delta SCF criterion. Two energies of successive iterations varying within 10 to the power minus x. X can be 10, 20, 30, 40, 50. Okay. So the moment you are satisfying that criterion, you say that you have reached the minimum.
It is true. So actually for low dimensional system, when we are dealing with small molecules or clusters, in that situation, each of the atom in the system, it has more degree of freedom, right? So my question was my concern was regarding that only, means when we do the calculation and find out the ground state of any system, it is found to be reported in different literature that sometimes the ground state reported by some other studies, they basically do not match with each other.
Yes. That all depends upon how efficient are your methods and the mathematical algorithms used to detect the minimum. Okay, so this is not a very well understood area. Okay, the minimum, you can have certain local minimum where you can get trapped. Okay, you may not be reaching absolute minimum. Okay, these are
it may also depend on the system, right?
Yes.
Constituents.
Of course. The potential energy surface can be shallow. You can be going around and around from a certain local minimum and not getting out of it. Okay, so there are techniques which are still being developed, but then the saving grace is that you have from the wave functional theory for small systems very good results of energy and other things for the minimum, and therefore if you are able to simulate with these methods those values, then for the larger ones, if you encounter some special problems, then again you have to take up that as a special case and try to solve it mathematically. Okay, so therefore, essentially what one does is one goes on varying and maps in which direction it is moving in the energy landscape, and then you take it from there in terms of a Taylor series expansion. Okay, so this is a mathematical, it's a computational, it's an algorithmic problem, and there are some very good methods to actually detect the minimum, to detect the absolute minimum and to differentiate the local minimum with the absolute minimum and so on and so forth.
Thank you very much, sir. Thank you.
You're welcome.
So, Jyotirmay Dev has a question. Jyotirmay, you can unmute and ask the question.
Hello.
Yes, you are audible. You ask.
Yeah, sir. I want to know that we are getting density. Now, from density, we are calculating the wave function.
We are not calculating the wave function in density functional theory. In density functional theory, that is the whole idea, not to calculate wave function. Just work with density and calculate the properties from density alone, including the total energy. The wave function part comes out as some kind of a misconception in the density function theory, because to generate density in the Cohen-Sham formalism, you introduce some kind of functions. The sole purpose of those functions is only to give you density. Okay, so those functions are not the wave functions, right? Their role is to only generate the density, and density is what is the key parameter of density function theory. So we do not deal with wave functions in density function theory. We deal with directly the densities. This will become more clear when we understand in the next lecture the foundation of the Cohen-Sham model.
Okay, sir. Thank you. Sir, another question is that when we are solving Coulomb equation, we are getting basically Coulomb orbitals, and if we calculate Coulomb again, then whether it is actual Coulomb because we are not considering the molecular orbitals.
No, see, let me tell you, it has been repeatedly highlighted by Walter Kohn himself. And I'll quote him. He says, when he gave the Cohen-Sham formalism with his postdoctoral colleague Lou Sham in '65, he said that I have thought deeply about it. The only purpose of the Cohen-Sham orbital is to give you the Cohen-Sham densities. These orbitals have no other physical meaning. However, because those orbitals are there, because we have been groomed for so many years in the molecular orbital picture, we want to also use Cohen-Sham orbitals as the other orbitals like in molecular orbital theory. And the two results are not very different. However, these orbitals represent a fictitious non-interacting system. These orbitals are a single determinantal expression of the so-called wave function, if you might want to compare it with the other Slater determinantal wave function of the wave functional theory. But the point is that the total wave function, if you can call a total wave function here, which you cannot in principle, as Kohn and himself has pointed out, but if you write the determinant of the occupied Cohen-Sham orbitals, then that single determinant is the one that is describing the density, because the occupied Cohen-Sham orbitals, when squared and summed over by multiplying with the occupation number, give you the density. It is the density which is used as a parameter everywhere in all the property determination. The orbitals used in the single determinant are not the orbitals of any other orbitals which we know. These are the orbitals which include the full exchange correlation in it. Okay, and therefore these orbitals are not the usual normal orbitals. These are all some kind of a mathematically convenient set of orbitals which are introduced into the Cohen-Sham scheme so as to be able to calculate the densities, and that's it. It is the density which is crucial. There are several papers, even by good papers by people like Hoffman and others, who show that these Cohen-Sham orbitals are very, very close to the even better than Hartree-Fock orbitals and this and that. But those orbitals have not any physical significance other than the fact that they are squared and summed and used to calculate the density. That's it. It is the density which is the key parameter.
Yeah.
Thank you, sir.
Well, so now it's time for the second lecture. So before that, sir, thank you very much for an excellent, and I can say that was the complete course on the Hohenberg-Kohn theorem.
Thank you very much.
You started from the prerequisites required, like the variational principle and the wave function, and exactly in parallel you showed how it was in the wave function theory and now it is in the DFT. That was a very important part, sir.
Thank you very much. Thank you. I will share my slide, my presentation with you, because you can probably distribute to all the participants.
Thank you. It will be
You're
helpful
welcome.
to all the participants. Thank you very much, sir. And it will be helpful for our future generation students, sir, as
You're
well.
most welcome.
Because we have one unit on DFT in our molecular physics course here.
Yeah, so well, that's the whole purpose of workshops like this, which is very, very important. So I'll be very happy to contribute. Thank you.
Yes, sir. Thank you, sir. And I, on behalf of the organizing committee, I express my gratitude to you, sir, for your excellent lectures and kindly sparing your time for us, for our students and participants, and look forward to your second lecture tomorrow. So participants, if you have any question or you have anything to ask, sir, he will be available tomorrow. The first lecture he will be giving again tomorrow, so you can ask your question there. Thank you very much, sir.
Most welcome, certainly.
Sir, Professor Thakur has joined, I think.
Oh, wow, very nice.
Yeah, thank you, sir. Thank you very much, sir.
You're welcome. You're welcome.
So now, after 2 minutes, we will have the next lecture. Professor Tanushree Saha Dasgupta Madam has already joined. So let us just take a 2 minutes break and then she will be presenting. And now I hand over my mic to my colleague, senior colleague, Professor Apti Deshmukhya. She will be moderating the second lecture.
A very good afternoon to all. We'll be waiting for 2 more minutes to start. You can have a short break.
Yeah, in this break, we can only drink water.
Yes, sir, because we cannot send you something, so you can only drink water.
I will also bring my water.
Yeah, that is better, I think.
Hello.
Professor Singh, kindly put off your presentation, sir. Stop presenting.
Oh, yes, yes, sure. Sorry. Yes. Is it gone?
No, sir.
No, sir.
Not yet. Oh.
Please go there and then, yeah, stop presenting. You click, yeah. Thank you, sir. So, Dr. Shukla, I think it's almost like it's a time, right?
Yes, ma'am. Yeah. Participants are here. So
Participants are here, and Madam is also here, I guess.
yes.
Yeah.
She went for a glass of, bottle of water. That's it.
Yeah.
Okay. So, a very good afternoon to all. It is my privilege to be able to introduce Professor Tanushree Saha Dasgupta. Professor Dasgupta works. I will just introduce her in very brief because everyone is waiting to hear her. Professor Dasgupta works in the area of computational condensed matter physics, material science, and a major thrust of her research is in the application of first principles of electronic structure calculations to understand the physics and chemistry of novel and complex materials. Professor Dasgupta has obtained her PhD degree from Calcutta University in the year 1995, and she was a postdoctoral fellow and visiting scientist in ONERA Paris, CNRS France, Max Planck Institution Stuttgart, IISc Bangalore, etc. Professor Dasgupta joined SN Ghosh National Center as a lecturer in the year 2000, and she is currently a senior professor and director. It's an additional charge in the same institute. In between, she was the Satyendranath Chair Professor at Indian Association for Cultivation of Science, and head of the School of Mathematical and Computational Sciences there. So far, she has guided 14 PhD students and published more than 250 research papers in different peer-reviewed journals. She is a fellow of American Physical Society, World Academy of Sciences, Indian Academy of Sciences, National Academy of Sciences, India, and West Bengal Academy of Sciences. She is a recipient of Swarnajayanti Fellowship, MRSI, ICSC, Superconductivity and Material Science Annual Prize, J. Rajaramanna Prize, P. Shittal Memorial Award, Dr. APJ Abdul Kalam HPC Award, and J.C. Bose Fellowship. She headed the Max Planck India Partner Group, Advanced Material Research Unit, and Thematic Unit of Excellence on Computational Material Science at S.N. Bose National Center. So with this, I would like to welcome Professor Dasgupta to the conference formally, and I would like to request her to please start talking to the participants who are eagerly waiting to listen to her.
Thank you very much.
Over to you.
I hope you can hear me and see me.
Yeah, it's perfectly fine.
Yeah. So let me start by thanking the organizers for this kind introduction as well as the invitation. So without wasting much time, let me share my screen. Is it the entire screen? Can you see my screen? Is it visible?
It is coming. Still, I can't see it. Yeah, it has come.
It has come. I'm just making it full screen. Okay.
Yeah, it's there.
Okay. So I slightly changed the title compared to what was announced, but theme remains the same. It is the title is Quantum Matter, Quantum Materials by Computation, Challenges and Opportunities, because I think there is a great opportunity in this particular topic. And as announced, I belong to S.N. Bose National Center for Basic Sciences, which is situated in Kolkata. And this institute was established in 1986 by the Department of Science and Technology to honor the life and work of Professor S.N. Bose, in whose name half of the fundamental particles of this world, namely the bosons, are, and which basically has a very big foundation stone of the quantum mechanics. So the topic of quantum materials is very relevant, particularly given the institute and the name associated with this institute. So quantum science and technology in general has been in focus in recent time. How can we just kind of shift this one? Okay, thank you. So there is a worldwide effort, in recent time, a great attention has been given to this particular topic. How could quantum technologies transform our society? And it's, as I mentioned, it's a worldwide effort. For example, the funding agency in Canada, Sep’2021, that basically has put together the most brilliant minds from across the globe, as you can see, from US, from France, from Germany. And all of them are really, really pioneers in their field. So they have put together these scientists from different parts of the world and with varied expertise to address how could quantum technologies transform our society. And as you can see, this is actually a hand-holding of scientists from different parts and also with a very different background and expertise. So, for example, in University of British Columbia, they have basically established a center on quantum materials. and which is where the contributing institutes are the Max Planck Institute in Germany, the University of British Columbia, University of Tokyo. So you can see that the three institutes from three different parts of the world, they have come together to build this center. And in US, there is a very big drive on this research on quantum science and technology, specifically with quantum materials. And one such example is the consortium they have built to look into the 2D crystal. Just to this gives you just a flavor how much the activities are all around the world in this specific topic. And of course, India is not lagging behind in this race. And the quantum technology has been given a massive boost in India's latest budget given by our finance minister, where it was announced 80 billion rupees over 5 years budget as a part of the new national mission on quantum science and technology. So quantum science and technology, especially quantum technology, has been in focus, as I said, and various different platforms has been discussed for that, starting from superconducting loops, trapped ions, silicon quantum dots, topological qubits, diamond vacancies. Many different platforms have been discussed as a suitable platform to kind of design quantum technology. However, there is a very big role of materials in this entire process of designing, because information is physically encoded in materials. So if you have to have some kind of information processing, doing manipulation with this information, you need to first implement it in some material. So this is basically kind of the workflow of the quantum technology platform. So on the way to the quantum technology, new physical concepts, phenomena, functionalities, and materials are expected to be explored. So one might have a theoretical concept, like many of you must have heard the word quantum computing. And as I said, this quantum computing can use different kind of theoretical concepts like Majorana particles. But for this concept realization, you need to have different kind of system in mind, like topological superconductors, superconductor ferromagnetic junctions, oxide interfaces, etc. And what that basically boils down to is the center point of today's discussion, namely the materials design, because shortlisting of materials candidate that will show such kind of, let's say, topological property, magnetic property, or superconducting property. So once such a shortlisting is made, of course, that leads to then the laboratory growth and characterization and the final implementation, the material specific implementation that will help this quantum technology platform development. So let us go back and make some general statement about the importance of material. The importance of materials in human civilization, I am sure all of you are aware of it. It is so much so that different ages of human civilization are named after one or another, starting from the Stone Age, Bronze Age, Iron, Plastic Age, to the modern age, which is that of the Silicon Age. And it was the foresightedness of the Italian philosopher, painter, and also a scientist, because he actually envisages that the future age is going to be the design materials. So the quote from him was, when nature finishes to produce its own species, man begins using natural things in harmony with this very nature to create an infinity of species. So that means the nature has given us certain material species, but then human being basically works on top of it and create and manipulate to create new functionalities, new materials. So that's a design materials. And quantum materials, to some extent, falls within this class. What are quantum materials? So these are materials which exhibit physical properties whose description actually require quantum mechanical models. For example, of course, at 0 Kelvin, you have the quantum fluctuation and everything should be decided by the laws of the quantum. But there are materials where even their finite temperature properties, description actually required the description by the quantum mechanics. For example, the superconductors, the magnets, the topological insulator, the multiferroids, all of them are finite temperature properties, but they exhibit all these manifestation of quantum mechanics even at the elevated temperature. The properties which are dominated by quantum fluctuations, quantum entanglement, quantum coherence, topological behavior, in short, the manifestation of quantum mechanical effects. Now, understanding and prediction on quantum materials is actually a completely multidisciplinary problem. It, for example, involves synthesis, characterization, design, fabrication, prototypes, and most importantly, modeling. That is where is the big contribution of the density functional theory. So it is a hand-holding between experimentalists, theoreticians, and the simulation people, namely in this specific case. Of course, there can be different kind of simulation, but the simulation that we will talk about will be all density functional theory-based simulation. But what I'm going to do in the remaining time of today's talk is to impress on you how density functional theory can be used in an intelligible manner to interface with these experimentalists, theoreticians, to result into an understanding and prediction of this exciting class of materials. So we, as I mentioned already, we'll focus on the third vertices of this triangle, namely that of the simulation, and specifically the simulation in which the density functional theory, together with some associated tools, actually will be used. So basically what we will focus on is the theory-based computation, and these are all high-performance computing, and this basically shows the setup of a high-performance computer, which consists of all the different CPUs put in a blade and all connected by some internet so that they can interconnect so that they can talk to each other. And of course, there are very powerful high-performance computers, and which are measured, of course, with the peak performance, and there are several 100 teraflop or even more, and I have given some representative places that basically houses such a high performance compute cluster. And again, the government has been very, very proactive in this domain, because they have understood the power of this high performance computing. And now there is a mission which is a national supercomputing mission, and whose goal is to basically install petaflop machines at different corners of this country under a national supercomputing mission. And already, one in IISER Pune, one in JNCSR, one in IIT Kanpur, another one in IIT Kharagpur, they are already has been implemented. And these will be made open to the users across the country. And still few of these centers are in the process of coming up. So I just want to impress on it, the government has taken a keen interest on such kind of computation, and large amount of money is devoted for it. Now, as I said, the simulation or the calculation we will talk about in today's lecture, these will be primarily the electronic structure calculation. So why we are interested in electrons? Because many of the properties of material are actually strongly dictated by what the electrons are doing. Because it's the electrons that is the glue that binds the atom together. So we have to have a good knowledge of what these electrons are doing. So density functional theory basically provides us, I'm sure you have been exposed to the theory of density functional theory. In fact, I could listen to only the remaining part of Professor Sen's lecture, and I can see that there are further lectures of Professor Sen on the density functional, specific topic of density functional theory. So I'm sure you are getting exposed to that. Today's lecture, my specific lecture, is to show you, without getting into the theory and with the idea in mind that you will be exposed to the details of this theory, showing the application, what it can do with such kind of theory if you use them in an intelligible manner. So the density functional theory provides us a way to calculate the electronic properties in an ab initio or first principles way. So why and what is the first principles approach? It basically gives a way of calculating the properties, I mean the properties associated with the electronic properties of material before it can be tested in a time-consuming and costly laboratory experiment, which actually greatly limits materials discovery. And this approach, being first principles in nature, it retains all chemical and structural information, because to have such a calculation, all you need is the information of the chemical constituent or composition of the material and the structure. The structure, of course, even in the modern density functional theory, you can even predict the structure of a material. And most importantly, it provides the microscopic understanding, which of course the experimental study is not able to provide. And this is a kind of a flow chart of the density functional theory calculation, where you basically solve a Coulomb equation, which is shown here, which looks more or less like the Schrodinger equation that you are more familiar with. But there is a very big difference, because normally in a Schrodinger equation, you have a potential that is independent of this wave function. But in this case, the potential actually depends on the density of the electron, and the density of the electron is connected to the wave function that appears in this equation. As a result of that, you can actually easily imagine that since the wave function is the output of that can be obtained by solving this equation, while the input, the potential, also depends in a way to this wave function through this electronic density. So therefore, the whole thing should be solved in a self-consistent manner. That is the key thing of such an approach, where you start with the guess value of the potential, normally the atomic potential, and then in this self-consistent cycle, which basically oscillates between solving such a Coulomb-like equation and the Poisson equation to get the potential once you know the density, and iterating it until and unless you minimize the force through this, the energy through this. And if you are also including the structural optimization, you can also basically minimize the force. And once you do that, then if you are really converged, then you can calculate the various properties. So what are the properties you can calculate? One is the structural stability. Since you can calculate the total energy, you can, for example, compare a material which can form in a BCC lattice or FCC lattice. You can compare the energy of this material in a BCC structure and SCC structure and compare their energies. That way you have an information of the structural stability. What you can calculate, very often it is calculated within density functional theory, although rigorously density functional theory is a method to calculate total energy, but people do use density functional theory to calculate the band structure, which is basically the energy dispersion, the K versus energy plot. And since you can calculate such a band structure, you actually have access to optical properties, because from the band structure, you can actually calculate the density of state and the joint density of state, and then through the matrix element effect, you can calculate the optical properties. You can calculate the phonons both in harmonic and quasi-harmonic approximation, which will give you access for calculating the Helmholtz and Gibbs free energy. Of course, all these calculations are T equal to 0 Kelvin calculation, but you can also have an access to finite temperature through ab initio molecular dynamics calculation, which unifies quantum mechanics with molecular dynamics. In such a kind of scheme, you basically separate the electronic degrees of freedom and the ionic degrees of freedom. The ions being much heavier, they can be actually handled by solving a Newton's equation, namely the classical mechanics, where the electronic degrees of freedom are obtained, are handled completely quantum mechanically by solving such kind of a Schrodinger-like equation, namely the Kohan equation. And these two things are connected by the Kelvin-Feynman force. So the force acting on the ions are calculated in a completely quantum mechanical way from calculating the electronic energies, the change in the electronic energies by the displacement of the ion, and from there calculating the force. This kind of framework also actually allows us to handle the strong electron-electron correlation. For example, the density functional theory, which is exactly in principle the most difficult part of this density functional theory, is the handling of the exchange correlation function. All the unknown thing is basically dumped into such a kind of exchange correlation function. And then you basically do different kind of mean field approximation, like local density approximation or generalized gradient approximation, all of them which are quite okay to apply to materials with weak electron-electron correlation effect. When the electron-electron correlation effect becomes strong, for example, in a transition metal oxide, as we will actually discuss a lot, then you have to go beyond this framework of local density functional light theory, and that can be handled within the framework of density functional theory with some supplemented Hubbard U-like correction, the theory that goes with the name as DFT plus U, and we shall be using very often such kind of theory because we will be basically dealing with transition metal oxide very often. So the first category, so what I'm going to do basically discuss 3 different category of problems that you can handle by intelligent use of density functional theory. The first category of the problem that I will discuss is understanding materials properties, namely the structure property relation. And the first example that I will take for it is the Q-print superconductors. So what is a superconductor? Of course, we know what is a conductor. If you have a conductor which basically conducts electricity from one end to another end, and of course, if you lower the temperature, your resistivity decreases, but it never vanishes, however low is the temperature, because you have some residual scattering from the impurities. But in a superconductor, below a certain temperature, of course, your resistance vanishes, and that gives you the name of superconductor. And as you can see, when this superconductor were actually discovered in mercury, elemental mercury, you see that the transition temperature, superconducting transition temperature was really low, 4.2 Kelvin. So it is a great technological advantage to have such a kind of superconductor, but we need to have this transition temperature raised to a certain level where it can be useful for day-to-day application. And what is shown here is over the years, many different compounds have been tried to make in superconductor with a goal to raise this transition temperature higher and higher and higher. And as you can see over the year, of course, this temperature has been made higher and higher and higher. And of course, the compounds have become more and more complex, starting from this elemental mercury that has become 2-component, 3-component, 4-component, etc. And basically, the compounds that we will focus on are these compounds, which are all copper oxygen based. So that showed a possibility that indeed you can find some compounds for which the transition temperature are pushed up to the scale of 100 of Kelvin. And this is a phase diagram which is common to all these compounds. The common between all these compounds are they are based on copper and oxygen. Two chemical ingredient is common among all these compounds. And they all have a very similar phase diagram. What is this phase diagram? You have temperature on one axis, the y-axis, and in the x-axis, what you have is a doping, the whole number of holes that you can dope in this compound. The superconductivity appears only upon doping hole. This material, if there is no doping, this is an antiferromagnetic insulator. Increasing the doping, this antiferromagnetic insulating phase disappears, it becomes a metal, but some kind of a very strange metal. And then the superconductivity appears and it has a dome-like shape, as you can see, with the maximum Tc at some optimal doping. So far, so good. But you find that there are many different copper oxide compounds and their structures are pretty similar, which I'm going to discuss in the next slide. But this maximum Tc, which is Tc at optimal doping, it actually varies between different compounds. It varies so much. For lanthanum compound, it is some 40 Kelvin, while for mercury compound, it's more than double, it's 90 Kelvin. So what does this material dependence come for? Can density functional theory like calculation help us in answering such thing? In case there is any question, I can't actually see because I'm in a full screen mode. But if anybody has any question, possibly you can ask by unmuting yourself. Is there any question so far?
Yes, ma'am. Rajesh Yadav has a question.
Yes, what is the question?
He has not asked the question, he has raised his hand. Rajesh?
Should we take the questions at the end?
Hello, ma'am.
Yes, ma'am. I think it would be better if we take the question in the last.
Yes, I'm asking some questions to you. What is the exchange correlation?
So can we take it at the end of the talk?
Yes,
Because I'm in full screen mode. It's very difficult. I can't see the raised hand or anything.
Please, can you hear me, Vaishma?
Yes, I can hear your voice.
Yeah.
Can
Yes,
we
MR Kannan, it is better if you ask the question in the last.
Yes. Oh, okay, sir. Sure, sir. Okay, sir.
Okay, so let us continue. So this is the crystal structure of this copper oxygen based compound. We have the copper atom, which is shown with the red color, which is surrounded by 6 oxygen. 4 of these oxygen are in the same plane as that of the copper, and that gives the layer structure of this compound. We have these layers of this copper oxygen plane, as it's shown here. And then you have also oxygens which are out of plane. And these oxygens are known as apical oxygen. So you basically have these copper atoms surrounded by 6 oxygen, which forms like a copper-oxygen octahedra. And these octahedrals, they kind of corner share to give rise to these layers. And then you have stacking of these copper-oxygen planes. And in between, for example, you can have lanthanum or some mercury or barium. And what is shown here basically is the band structure, which many of you are actually familiar with, which is the plot of energy versus the wave number or the momentum, the wave vector. So these are basically the high symmetry points of your Brillouin zone. It's plotted like that. The zero of the energy is set at the Fermi level. But you find that at the Fermi level, there is only one band that is crossing the Fermi level, the zero energy, for both compounds. In that way, their band structures are actually pretty similar. But there are actually some delicate difference between the two. And that basically shows up if you look at the Fermi surface. What is a Fermi surface? That is basically a constant energy surface where the energy is set at the Fermi level. For example, if I set the energy here, then what are the key points or the wave vector points that cuts this particular energy? That gives you this Fermi surface. So you can see the shape of this Fermi surface is actually quite different between these two different copper oxide compounds. In one case, this is much more rounded. In another case, this is much more squarish. Well, these are for the experts. But what you can actually calculate with such a kind of the density functional theory, you can look at the wave function that describes this single band. It is possible to do that. And then you look at these wave functions which describe this single band for the lanthanum compound and for the mercury compound. I mean, of course, this is a combination of the copper d orbital, which is like dx square minus y squared, and then you have basically the oxygen p-like thing. So it's a linear combination of these. But already you can say that for the lanthanum compound, this wave function underlying this single band is much more localized for the lanthanum compound and much more delocalized for the mercury. And what you can basically define is the extent of such a kind of function through a parameter which is a dimensionless range parameter R. And what is plotted here is the range parameter for different compounds. And for different compound, what actually is the crucial structural parameter that varies between different compounds is this distance between this pink plane to the oxygens which are out of it. So this distance for lanthanum compound is 2.4 angstrom, for mercury compound is 2.8 angstrom. And there is a kind of a correlation between this range parameter and this copper oxygen plane, this pink plane, to the apical oxygen, this outer plane distance, basically this distance. You can already see the moment it becomes very large, like 2.8 angstrom, already this thing has been saturated. This range cannot be made any further, longer. And what we did actually, we calculated the range parameter for all known high TC compounds, high TC copper oxygen compound. Since their TC is, the superconducting TC is very high, we call them as high TC cuprate copper oxygen compound. And you see, we didn't actually calculate their superconducting properties at all, because within density functional theory, calculation of such kind of which are very unconventional superconductivity in such copper oxygen compounds are very, very difficult. So we didn't even attempt to do that. So these TC, they are basically experimentally determined TC values. So this plot, in a way, if you like, is a semi-empirical plot where we, through density functional theory, calculated this range parameter for a range of compound and then plotted against the experimentally measured TC max or the TC at optimal doping. And if you follow, don't bother about the open symbols or this, half-hashed symbol. Just follow the completely solid symbol. You do see, considering so many different varieties of copper oxygen based material, there is a connection between this range parameter and the TC. So this is the property. This axis is the property which is measured, and this range parameter is connected to this copper oxygen plane to apical oxygen distance, which is a structural parameter. So that means that is the role of your density functional theory, like calculation, which is making a connection between this property which is measured and the range parameter which is actually connected to the structure. So therefore, it gives you a way to connect this structure and the property. So the message that you get, that to increase this TC further and further, you need to basically make this distance between the copper oxygen plane to the apical oxygen larger and larger and larger. Of course, we cannot make it infinitely large, because that is also shown here. Beyond certain point, it actually doesn't affect the thing, and there is a detailed physical reason why it cannot. But then you can go to, instead of having only one copper oxygen plane, you can put 2 copper oxygen plane, 3 copper oxygen plane, and by that way you can increase the TC even further beyond this 90 Kelvin of marker. Even there is a limitation. You cannot make it more than 5 layers, then the coherence of the sample gets lost. But these are matter of detail, but it gives you a way to connect the structure to the properties. The second example that I would like to talk about in this context are low-dimensional quantum spin systems. So what are these? These are again transition metal oxide with small spin. That means the transition metal ions like copper 2+, vanadium 4+, titanium 3+, which has a spin which is small, spin half, because their d occupancy is such that either you have a single d electron or you have a hole in the d manifold. Or you can take nickel 2+, vanadium 3+. So these are basically either 2 electron or 2 hole that will generate the s=1. So these spins are small. And although these compounds are all 3-dimensional, important magnetic interaction, that means how does one spin talk to another spin, those magnetic interactions are highly anisotropic. There are important magnetic interaction only in 1 or 2 dimensions. They don't interact in all 3 directions equally. So that gives the name as low dimensional. I mean, these compounds don't get confused with graphene or any other thing, which is structurally low dimension. Here it is low dimensionality arises only when we look at their magnetic behavior. And this actually provides a fascinating playground to study properties which are dictated by quantum fluctuation, because the smallness of the spin makes the effect of quantum fluctuation very, very important. So what is not known is how exactly this spin situated here will talk to this spin there. And there is a very big role of this microscopic investigation by doing first principles calculation. Of course, with these first principles calculations, since you know how one spin talks with another spin, you can basically generate the underlying spin model, which is shown here. For example, this underlying spin model can be like a spin chain, can be a 2-dimensional spin placket, can be a ladder-like object. Many different such spin models are possible. But the role of the, the job of the density functional theory basically ends just by giving such kind of the magnetic interaction. solving of such spin model, we need to actually invoke to some many-body method. And that is exactly what we try to do, where we couple the density functional theory. It's a two-step process. We use the density functional theory to arrive to an effective spin model, which we then solve with a many-body method like exact diagonalization or quantum Monte Carlo, etc. So again, this is a picture where we have this wave function of this magnetic orbital, and we see how the magnetic orbital or the wave function of this magnetic ion at one side makes an overlap with that at the next side. That gives us the idea of this magnetic model, and by many-body method of solution of such magnetic model, one can calculate, for example, the magnetic susceptibility, one can calculate the spin wave spectrum, and they can be compared with the experimental data, which is shown here, for example, with the solid curve. So again, these are properties which are measurable and measured in the experiment. Density functional theory helps in connecting the structure and chemistry through such properties. Of course, if you just use density functional theory, it's not enough. So you need to couple it to such many-body method to arrive into such kind of a physical picture. So I think density functional theory, if used intelligibly, it can be used as an effective tool in uncovering structure-property relationship. The next class of problem that I would like to discuss is prediction of new functionalities in known materials. So far, what we have talked about is where the material is known, meaning all these copper oxygen compound or the transition metal compounds, they have been all synthesized, they are known. Their properties have been also measured. So both properties and the material both are known. Now, in the second category of the problem, what we are going to discuss, the materials are known, but through density functional theory and the associated computational tool, we are going to predict some new functionalities in the known materials. Since the materials exist, it is for the experimentalist to verify these functionalities that is predicted by the density functional theory. And for that, what I'm going to take as an example to demonstrate the applicability of the density functional theory to such class of problem is that of the metal organic complexes and coordination polymers. So what are these? These are, again, I have basically a transition metal ion which is sitting at the center of this molecule. And this is a metal organic. So that means all these things that you see here, kind of extended object, they are basically some organic ligands associated with this transition metal ion. So this is a molecule which is kind of a metal organic molecule which has a combination of both metallic, inorganic, metallic side and these organic ligands. And since these ligands are organic in nature, they are very flappy. They can be actually perturbed very easily by an external perturbation. Like temperature, as is shown here, or pressure. The pressure can be chemical pressure or mechanical pressure, by light radiation, by magnetic field, by substrate. By changing that, what do we achieve? For example, let's assume this metal ion, transition metal ion, at the center, this red ball, is iron 2+. So iron 2+ has 6 number of electron in its D shell. Now, since this red ball is surrounded by 6 blue ball, the D levels, they split into 3-fold degenerate T2G level and 2-fold degenerate TG level. Now, how do I arrange these 6 D electrons in this T2G and EG level? One possibility is I pair them up so that I have a T2G level which is completely filled with 6 electrons. In this case, the total spin is 0 and this is known as a low spin state. The other possible way is I take 2 of this green arrow and upgrade them to this EG level. In this case, I have 4 unpaired electrons and the spin is equal to 2. So that is known as a high spin state. Now, what decides whether the molecule will be in low spin state or in high spin state? Of course, depends on this energy difference. So to basically promote these 2 of this green arrow to this higher level, you need to overcome this energy difference between T2G and AG. But in this configuration, you have maximized the spin. And there is this Hund's rule, if you remember your quantum mechanics course, which actually tells you that your atom likes to maximize its spin. So therefore, such a configuration is favored by Hund's rule. So therefore, it's a competition between these energy difference and the strength of this Hund's coupling, which is known as JH. So clearly, this Hund's is an atomic property. I cannot change this. But what I can change is the energy difference between this level and that level. And that is possible because that is dictated again by this structural parameter, the distance between this red ball and the blue ball, or this bond length. The larger is this bond length, smaller is this energy difference. By increasing this temperature, what you are going to do, you are having an expansion of the bonds, so therefore making this red to blue ball distance larger and therefore reducing this energy difference. And that actually helps to promote these 2 green to this red. So as a function of temperature, one can therefore have a low spin to high spin transition, and this is quite popularly known as spin crossover transition. Now, what is important that, as you can see, this whole phenomena of spin crossover is a kind of a molecular phenomenon. But from a molecule, can we make them like a polymer by connecting one molecule to the next molecule? By that way, this spin crossover from low spin to high spin, I can make it cooperative. And if I can make it cooperative, in the sense that the spin crossover that takes place in this particular metal site, this metal site, and this metal site, and this metal site, they all happen at the same time. And if I can make them really, really cooperative, what can happen that the spin crossover becomes really like a spin first order spin state transition. And very often that actually shows up with an associated hysteresis of it. So what does it mean? That if I'm heating up this material, then the temperature at which this spin crossover takes place, and when I'm cooling this material, the temperature point where the spin crossover takes place, they are different. So therefore, depending on whether I'm at the cooling path or heating path, I can be either in the low spin state or the high spin state. So therefore, your material basically remembers whether we started from a low spin state or we started from a high spin state. So your material can be used as a memory device. And this is seen in the experiment, as you can see, that whether your material is in a low spin or high spin state, since their optical gap changes, their color also changes. So depending on whether I'm at the heating or cooling path, at the same temperature, I can actually have a change of color of this material. So therefore, if one can really devise such a thing where the hysteresis, the width of this hysteresis is large enough and the midpoint of this hysteresis is right at the room temperature, it will be of a lot of attraction to devise a picture. Now, what can be, so I have already said about it, this large cooperativity is very, very important if I can make such a kind of a polymeric compound, in contrast to a molecular crystal where I have some isolated molecules. Now, what are the possible candidates showing such kind of cooperativity that I have just mentioned? I already talked about the polymer, where you can make like a chain in 1 dimension, 2 dimension, or even crisscross in 3 dimension. That is also possible. And these are known as coordination polymer. Or I can have what is known as hybrid perovskite. So what are hybrid perovskite? Many of you have heard about the word perovskite, which are inorganic perovskite, which is of general formula ABX3. X very often is oxygen, B is a transition metal, and A can be either an alkali or alkaline metal or a diamond. So this is a hybrid perovskite where I also have some kind of a metal at the B side, but at the A side, instead of a alkali alkaline or cation or the other, what I have is actually an organic molecule. And at the ligand side even, which for example in an inorganic case can be either oxygen or halide, it can be even an organic molecule. So in such a case, if you can imagine that if I put an organic molecule here at the connecting thing by applying pressure or temperature, I can easily change this. And basically the size of this octahedra can be changed, and therefore I can stabilize either in low spin or high spin. And since they are kind of connected to each other, I can make this whole phenomenon cooperative. As I already explained, they can be used like a memory device. So these are basically materials of great application potential. However, there are challenges for material-specific predictive theoretical description, transition metal ions, and there is a strong electron open D shell of the metal center, which I already talked about a little bit in terms of this exchange coordination function. The complex geometry of the material, since we were dealing with some organic molecules and etc., and the polymers, very often the unit cell contains several hundreds of atoms. So making the computational cost very, very expensive. Most important is also the ability to capture the electronic and structural changes under external perturbation. As I say, we are going to, with temperature, with pressure, we are going to basically perturb the structure, and which would cause this low spin to high spin transition. So that means your method should be capable to follow the electronic and structural changes under the external perturbation. And what we are going to do is to apply the density functional theory supplemented with a Hubbard-U correction, and to take into account the finite temperature effect, we will make use of the ab initio molecular dynamics. And these materials has been synthesized like these hybrid perovskite, which are Haran-based hybrid perovskite with some format ligand and some protonated amine put at the A side. So these materials exist, but nobody looked at the spin crossover properties in this material. And as you should see here, we have done this calculation where we have taken these materials and have applied the hydrostatic pressure. And you can see, depending on increasing or decreasing pressure, there is a spin crossover transition or spin state transition with associated hysteresis. And depending on which protonated amine we put at this A side, the width of this hysteresis can be also manipulated. So this is a prediction, a completely new prediction obtained through density functional theory calculation, which of course can be suggested to an experimentalist to look into these functionalities in these known materials. The other example is that of this polymeric compound, There also we, through temperature effect, we looked at this hysteresis and we came up with this suggestion that there will be actually a temperature dependent spin crossover transition with a hysteresis. We also considered some bimetallic polymeric compound, the coordination polymer, and there we applied a temperature pressure combined route. Through that, what we predicted is not only a high spin to low spin, but a high spin to intermediate spin to low spin. The intermediate spin of iron is equal to 1, and which is very rare, intermediate spin of iron is almost not known, except other than under pressure in Earth's crust. But this is also a pressure thing, and here instead of Earth's crust, where it is completely inorganic, here you have an organic component. And not only that here this was bimetallic, so in addition to iron, we also have niobium, and through this combined temperature pressure, we could also predict basically the relative alignment of iron spin and niobium spin can be also parallel or antiparallel. So through this, what we predicted is a new spin state of iron and also tuning of magnetic alignment from antiparallel to parallel between iron spin and niobium spin. So these two results that I have discussed, this is a completely new prediction of these functionalities in some materials which exist. So these should guide an experimentalist now to search for this functionality which has been predicted by us. So therefore, such kind of the application of density functional theory assisted method helps us in designing new functionalities, predicting new functionalities. The last set of examples that I will talk about is predicting new materials altogether. Since the density functional theory has a lot of predicting capability, so far we have been little ambitious and said that some material existed. Can we predict new functionalities in them? Now we want to be even more ambitious and say, can new materials be predicted altogether? We need, of course, new materials with targeted property. We want to, that is your design material stage, where we have some properties in mind, but we don't know what are the material that will exhibit such property. Can density functional theory predict such new material? And here, of course, there are the examples that I like to talk about are the magnetic materials. I mostly talked about magnetic materials like the spin crossover and all that. Those are magnetic properties. So of course there is an enormous technological application. I don't have to really impress on that, starting from electromagnets, electric motors, to generators, to magnetic storage like tape recorders. Every day, most of the things that we use have a magnetic component. However, there are also magnetic materials. You will be also very surprised to know, in fact, although the magnetic magnets are very important in our day-to-day life, among the known materials, the percentage of magnetic materials is very, very small. Apart from that, there are some technologically important magnetic materials with specific properties. For example, like ferromagnetic half metals. So we know ferromagnets where the spins are all aligned in the same direction. And most cases, they are metals. That means they conduct electricity from one end to another end. But there are also something which are known as half metals. What is a half metal? So these materials, since they are ferromagnet, they have a difference between spin oriented in the up direction and spin oriented in the down direction. Now this material is a metal in one of the spin channel, while in the other spin channel, it's an insulator. So these materials are known as half metals. What are the importance of that? Of course, for information passing, one can use the charge. Okay, that's the current passing. But one can now also think of a spin current. That means the information can be propagated not only in terms of charge, but also in terms of spin. Because you have 100% spin polarization of the carriers. And that has opened up a completely new field like that of the spintronics, which is highly discussed for the spin valve effect and central to the magnetic storage and sensing, because as I said, now you have an additional degrees of freedom to store information. And in making such kind of this spin valve and etc., what you also need is antiferromagnetic metals, which can be used as a spinning layer in spin valve devices. Now, antiferromagnets, which is a picture shown here, where the spins are antiparallel between neighboring sides, as is shown here. But there is a material challenge, because most ferromagnetic materials, they are metals, but not half metals. And most antiferromagnets, they are insulators, but they are not metals. So we need new materials which will be ferromagnetic half metals and antiferromagnetic. Can we suggest and predict such material can be? That is the question. And for that we decided to explore, because exploration is really the essence of the human spirit. So explore double perovskite. What are double perovskite? I already mentioned what is a perovskite. That is a general formula AbX3, and very often this X is oxygen. They are all oxides. You take this perovskite formula and make double of it. That is 2 times that of the perovskite formula. So if you make it 2 times, it becomes A2B2O6. Now, since there is B2, instead of 1 transition metal, I can actually put 2 transition metals, namely B and B prime, which are different. And then the structure is something which is shown here, where I have actually the ordering of this B and B prime alternately in all 3 directions. Of course, each B and B prime are surrounded by 6 oxygen, forming an octahedra, which a corner shared, and the A atom fills up the void that is formed by this corner shared octahedra. Why did we choose this specific class of material? The answer lies here, because many of these double perovskite that have been made, they are magnetic metals with a very high transition temperature, which is shown here. What is listed here is only the B prime combination. At the A side, you can put a divalent cation like strontium, barium, or calcium. Okay, so what is really interesting? So this is some kind of tables that were put in this review article, where I don't know whether you can see this because the lettering might be too small, but they considered basically all different combinations of B and B prime. And they considered at the A side putting either calcium, strontium, barium, or lanthanum, because these are the mostly all known double perovskite. They are all either at the A side, they have this divalent calcium, strontium, barium, or trivalent lanthanum. And you can see they have colored each of these boxes differently. The boxes are colored as green if this compound is made and exists. The boxes are colored in this blue if one requires a kind of a high temperature, high pressure synthesis to make this compound. Some special synthesis technique is needed. They cannot be made in ambient condition. Then there are red, which means an attempt was made to make this compound, but the attempt failed. They could not be made. The yellow ones are the combination for which the attempt was made. The compound was formed, but not in a perovskite structure. So this is a very useful, database of all possible compounds that of the double perovskite, different combination that have been reported in literature. But what caught our attention that many of these triangles are what? So which means these combinations have never been tried. Nobody has attempted this combination to be made. I mean, at least not reported. So there are lots of possibilities yet to be explored. Now that brings me to the question, can one use machine learning to predict this kind of unexplored combination? So this is a quote from the Nature article that was the title, Can Artificial Intelligence Create the Next Wonder Material? Well, the method that is followed, I'm just trying to say it in 1 minute, but of course this is a very detailed method. So the first step of this method is a database construction. So that means this database, for example, in the present example, will be the database of all known double perovskite that is being reported in literature. And this is known, each of the point in this database is known as an instance. Any compound that is known will be one instance. And we will come up with some attributes, meaning some quantities to characterize that particular compound or that particular instance in this database. And once we do that, of course, in this database, there is some pre-processing step because some of the data points will be a complete outlier, they needs to be removed. Some of the attributes, namely the quantities through which we are characterizing a given compound, that can be highly correlated. So that has to be removed also. These are pre-processing steps. So once you do that, the machine basically, which is the machine learning model, that basically learns from this pattern. This is nothing but a pattern recognition. That if something is black and of this height and of this dimension, it will show this property. So it is just like a pattern recognition. So this model does this pattern recognition. And we then use this machine learning model to predict new compounds. And once new compounds are predicted, we will be using some of the density functional theory tool to characterize this material. So as you can see that searching the literature, such kind of database is constructed. So we found some calcium-based 115, strontium-based so many, barium-based so many. So we had a database of some 641 compounds. We then had some attributes to characterize each and every compound, which is a point in this data set. And some of the attributes are structure related. For example, the ionic radius, you can define the ionic radius average at BB prime, their difference, their ratio. Something you can define which is known as tolerance factor, where also the ionic radius of the A cation and oxygen are involved. So these are all structure related attributes. There can be also chemistry related attribute like at the B and B prime site, whatever chemical component is there, what is their column, row, their valence difference, atomic mass, electronegativity, without doing any calculation, just from the knowledge of the compound and its structure, you can already have these attributes. Attributes, because one of the goal is to reduce the computational cost as much as possible. So these attributes are something which are very simple quantity, you can just find it from literature. And through that, you basically built up this model, which is nothing but, again, I'm repeating, it's just a pattern recognition. And then we scanned 412 new combination of BB prime for strontium, calcium, and barium at the A site. And of course, this model comes with also some predict confidence level in prediction. Since it's a pattern recognition, there is an associated level of confidence. So we could actually predict 33 compound to be strongly predicted at double perovskite. That means this BB combination, if it is tried, there is a very strong possibility it will appear in a double perovskite structure. For 60 compound, we had some moderate confidence. For 29 compound, the confidence level was such that it is unresolved. We could not predict with confidence whether if tried it will be made or not. And we also with confidence could tell that 54 BB prime combination, if tried, it will not form in a double perovskite structure. So that actually helps us in screening lot of combinations. So with that, once we have narrowed it down to some 33 compound, we actually calculated their crystal structure, meaning predicted their crystal structure, and also their magnetic and electronic property, which were completely density functional theory-based calculation. Crystal structure prediction, now it is not like looking at structural stability, because you don't know what underlying crystal structure or such a multi-component system is. And for that, what we used is an evolutionary algorithm, which is an universal structure predictor, where we start with some initial population of different structures. So you can see these are basically different space loop symmetry. Then we do some local optimization, which is done with completely density functional theory. Calculate the DFT total energy for each of the structure. Then select few of these low energy structure, which are called as parent. That's where the evolutionary part comes in, because starting from such parent, you use some of the operations like recombination, mutation to generate what is known as the offspring structure. That's where the evolutionary part comes. Then by hard constraint, you select the offspring. Then you have a new population where you mix some of the old structures with some of the new structure chosen from offspring. And then you rotate, you basically again iterate this scheme until and unless you find some few selected structure given by such evolutionary scheme. So this evolutionary scheme is a very general scheme. The DFT part here is in terms of energy calculation. Instead of DFT, you can use any other thing to do energy calculation. But for our purpose, we use the density functional theory, accurate calculation to calculate these features. And these are basically the different structures that we predicted for this 33 compound with their complete space group symmetry, atomic position, and everything. And then we did the calculation of the electronic structure and magnetic structure to classify these compounds in terms of their electronic and magnetic property. We could come up with several examples of ferrimagnetic insulator, ferromagnetic metal, but many of them we could predict what we were looking after was the ferromagnetic half metal. We found actually succeeded in finding one example of also antiferromagnetic metal. Other than usual antiferromagnetic insulator, and also some of the compounds turned out to be non-metal. So this is a very useful database for an experimentalist before going to the lab, trying out so many combinations. If such a kind of screening can be made in computer, that will be an extremely useful input, as you can already imagine. So therefore, I would just like to end with this. Material matters, and new materials in design is one of the hot topics of today's research. Quantum materials is a playground for future. I have told you both the challenges and the opportunities in this field. And this is acknowledgement to numerous students and collaborators. And I primarily listed the students and collaborators whose work I presented in my talk. And thank you very much for your attention. If there are questions, then I'll be happy to answer them.
Thank you, ma'am. Now I would like to request the participants. That was such a lucid talk, and you can just start interacting with ma'am. Yeah, the person who raised hand earlier, you can really put your question, unmuting yourself here.
Yes, actually there is a question by Dr. Tara Prasad. He has written in the question and answer.
Okay.
Yeah, he is writing, Namaskar, in the algorithm to design new materials. It was interesting. Could you please provide some more information about it on the development or presently existing designed materials and on applications?
Well, for the designing new material, what I showed is basically this is a combination of a machine learning method together with density functional theory. Machine learning method was to screen basically different possible materials candidates. And once you have done that, then we use the density functional theory to characterize its properties. So I don't know whether I could answer your question.
Dr. Tara Prasad, are you here? Dr. Tara Prasad, you can unmute and ask if you have any follow-up question. I think he is not able to unmute also.
Okay, no problem.
So
I think we can take that question. Somebody raised hand.
Yes, ma'am. So those who have raised their hands can ask the question. If there is any question, you can ask. Yes, Mr. Kannan, you can ask. M.R. Kannan.
Yes, sir. Sir, what is the exchange correlation?
Yes, so I don't know how much of density functional theory has been covered. In the density functional theory, the energy functional has different parts. Okay? Do you aware of this Hartree and Hartree-Fock theory?
Yes, ma'am. Yes, ma'am.
Yes, if you know the Hartree and Hartree-Fock, then in case of the Hartree, there is a direct part, which is the Hartree contribution. Then when you go to Hartree-Fock, there is an exchange contribution, right? Now, beyond the Hartree part, other than the exchange part, you also have the electron correlation part, because the electrons are basically interacting with each other, not only through Hartree part and the exchange part, but also through a correlation part. And people don't know how to calculate it. So whatever is unknown, that is basically clubbed into a functional, which is known as the exchange correlation functional. I'm sure Professor Shen is going to cover it in his talk, I think, which is tomorrow.
Okay, ma'am. Thank you, ma'am. But I have one question, ma'am. For inorganic material, why we which software which is best, ma'am? The ASP or quantum espresso, ma'am?
No. The point is that both VASP and Quantum Espresso just don't get into the software names. Both VASP and Quantum Espresso, they are all density functional theory based computer code. What is being used is the basis function, and the basis function in both VASP and Quantum Espresso is the plane wave basis, for which you use some kind of the pseudo potential construction. And the pseudo potential construction of VASP and Quantum Espresso are somewhat different. So it is up to you which one you want to use.
But now I am using Gaussian software, ma'am. But I can't use inorganic material in Gaussian software, ma'am. Why, ma'am?
What? Sorry, I did not get it.
No, ma'am. I am now I am using Gaussian software, but why I am using organic material only used in Gaussian software? Why not organic? Why not inorganic material, ma'am?
Yes, I understand your point. First of all, in case of your vase for quantum espresso, this is designed to be applied to a infinite crystal structure, okay, where you have a periodic arrangement of atoms, okay.
Yes, ma'am. Okay.
Gaussian, you can easily apply it to molecule. It depends on what kind of basis set you are using. The plane wave basis set is suitable when you have a periodic solid. Okay.
Oh,
The most
okay.
inorganic thing you are using possibly they are periodic solids.
Okay. Thank you, ma'am.
Yeah, hello. Can I ask one question?
Yes, yes.
Yeah. Tanushree ma'am, I'm Bulumani from Dibrugarh.
Yeah. How are you?
Yeah, I'm doing fine. How are you?
Oh, yes,
Yeah.
yes.
Okay. Actually, my question was, we are interested in studying some optical properties of some two-dimensional materials. So in that case, literature. This is the first time I'm going to do it, and I am trying with quantum espresso. Literature says that people are using hybrid functionals, as well as it is also suggested to use the perturbation ZW calculations. What is your comment on this? Yeah, what is your comment on this?
Yeah. So these are two different things. First of all, I mentioned already that the density functional theory is a method to do total energy. It is a method for ground state properties. Okay. On the other hand, whenever you have an optical properties, that means you are looking at the excited state property because it's a transition from one state to another state, right? So if you are really interested in doing a rigorous calculation, you should actually do a GW calculation, which is a method capable of handling the excited states. Or if you are doing a density functional theory, you should really look at the time-dependent density functional theory. Okay. So of course, people use even density functional theory to look at the optical properties, knowing fully well that density functional theory is meant only for ground state properties.
Yeah, so my query was, since I'm doing this for the first time, my query was because, see, when we get the band structure with our DFT calculations, we know that it gets underestimated, basically, because in case of optical properties, we have to look at the optical band gap. Yeah.
Yes, one is the issue of the band gap. Okay?
Yeah.
The band gap is underestimated in a DFT calculation, but again, when you talk about band gap, it is an excited property. Ideally, you should not use even density functional theory.
Yeah. At the same time, the ZW calculations are very much computationally expensive calculations. So my query was, say we have a set of say 5 systems, and we have calculated the band structures with our DFT calculations, and then if we do the say ZW calculations for one of the say pristine system, then for the rest of them, although I know that we cannot basically make general comment that the band structure is going to change in this patient, because ZW calculations are quite expensive, but still I need your suggestion. Instead of doing the ZW calculations for all the 5 systems, can we just do it for the pristine and get some idea how the band structure is going to change?
I don't think that is a very good idea. That which is computationally cheaper compared to GW is a hybrid method. Okay. So the hybrid actually corrects sometimes, sometimes it overestimates even the band gap. Okay. So if you are really concerned about just the band gap, then hybrid is a good method. But of course, the hybrid also doesn't tell you much about whether the band dispersions are correct. And for example, you look at the effective mass of this excited state. They may be incorrect, but good compromise will be to do the hybrid calculation.
Okay. For doing ZW calculations, I have come across two packages like Berkeley and Yambo. So do you have any experience on these, and can you suggest which one will be better, or means, of course, computationally little bit cheaper?
You can use the Berkeley. Which is a very well tested. I mean, GW calculation also comes with a different flavor, self-consistent or one shot. There are many different flavors of that, and the results also vary depending on that. So I think a good compromise will be, since you don't probably have much computational power, is to first do an hybrid calculation and see what you are getting.
Okay. Thank you. Thank you for your suggestion.
Thank you.
Okay.
Is there any more question? I think there is no question now.
I think so, even.
Yes.
So, on behalf of the organizers, I would like to thank Ma'am Tanushree for sparing her valuable time discussing, sharing with the.
Ma'am, sorry to interrupt. Just someone has just raised one hand.
Okay, but I cannot see. Okay, Rituparna Hajarika. Yes, please, Rituparna.
Good evening, ma'am. I have a doubt, ma'am. Actually, I'm very new to quantum espresso. I want to know about the phonon calculation. Actually, for extended, we actually know it that phonon calculation are a little bit expensive. Yeah, actually, so my cell, if I increase the size of the cell, and then it becomes more expensive. So without doing if we take 1x1 cell and calculate and do the phonon calculation, and is it necessary to do the same cell in 4x4 super cell? The same phonon calculation for super.
That depends on what kind of method you are using. So one method is known as the frozen phonon calculation. In which case, of course, within the frozen phonon calculation, you basically make some displacement of the ions. Okay. Now, if you want to do a gamma point phonon calculation, then of course your unit cell is enough. But if you want to have a phonon mode which is at the zone boundary, then of course you need to increase the cell size. So depends on whether you are interested in just the gamma point phonon or the full phonon dispersion. But there is also something which is known as the density functional DFPT, density functional perturbative theory. If you do that, then you don't need such a supercell construction. So it depends on which kind of method you are using.
So, ma'am, actually my structure is graphene. Suppose graphene is ma'am, it's single layer.
Even for a graphene, your phonon can be either if you want a full phonon dispersion or you want just the gamma point. So that will depend on that.
Okay. Thank you, ma'am.
Yeah. And I think, my email address is with you. So you are, you are free to share my email address if you have question over email. That is fine.
Yes, ma'am. I'll share your email ID to all the participants. And if any participant has any question, can ask directly to you.
Sure.
And contact you. And thank you very much, ma'am, for accepting our invitation.
Thank you.
Atri, madam.
Yeah, so as I was saying, it was a formal vote of thanks. So I would like to thank her for sparing her valuable time, sharing her experience and knowledge with the participants. And obviously, it is of immense value. And we hope that in future also we'll be able to get you in different academic platforms. And I would like to thank the participants to be here present. Without you, the program is of no value. So we stop here for today. Dr. Shukla.
Thank you. Thank you. Thank you.
Yes.
Thank you.
Thank you very much,
For
ma'am.
today, we are stopping here. And tomorrow we'll
Yes,
resume
today we
again.
will conclude here, and tomorrow at 2 p.m. we will reassemble here with Professor K.D. Sen's lecture. He will continue from the Hohenberg-Kohn theorem. So today he finished about the Hohenberg-Kohn theorem, and tomorrow he will discuss about the Kohn-Sam idea. So thank you very much, everyone.
Thank you. I am then disconnected.
Yes, ma'am. Thank you very much.
Thank you, ma'am.
Yes. So thank you, everyone, and good evening. Have a nice.
Yeah. So have a nice break till tomorrow and be here at 2 p.m. tomorrow. See you again then. Okay,
Thank
bye.
you, sir. Thank you, ma'am. Thank you. Thank you, sir.